Good morning to Ananda. So kindly confirm audio, video, and screen once. Kindly confirm the audio, video, and screen. Is it okay? Audio, video, and screen. Fine. See, till yesterday we have discussed about the power transfer equations, right? Power transfer equations, and we have seen varieties of problems in that. Okay. From this day onwards, as I said you yesterday, we will be continuing with the lossless long transmission line analysis. Okay, lossless long transmission line analysis. That's our next heading. Lossless long transmission line analysis. Lossless long transmission line analysis. So it is also very, very important topic for the GATE examination as well as for ESC examinations. So if any question comes from TND, particularly steady state analysis, there is a high probability of getting the question either from the topic of steady state power equations or from the topic of the lossless long line or simply long transmission line, what we are going to discuss. Okay, first of all, we studied in case of long transmission line, BSIS vector, so called sending end side voltage and currents, will be equal to ABCD parameters. What are the ABCD parameters of long transmission line? Cos H gamma L, ZC, sin H gamma L, and then we have 1 by ZC, sin H gamma L, and we have cos H gamma L. Cos H gamma L. This multiplied with the receiving end voltage and receiving end currents, VR. Like this you can see. Cos H gamma L, ZC sin H gamma L, 1 by ZC sin H gamma L, and then we have cos H gamma L. These are the ABCD of the long transmission line. Okay, let's recall these terms quickly. What is gamma and what is ZC? Gamma is called as propagation constant. Gamma, it is called as propagation constant. Propagation constant. And that gamma is equal to root of small z into y. Gamma is equal to root of small z into y. So that small z into y under root, we have written like alpha plus j beta. We have written that like alpha plus j beta, where alpha is in Nepers per kilometer and beta is in radians per kilometers. Right? Gamma, alpha plus j beta, alpha is in Nepers per kilometer, beta is in radian per kilometer. Okay, ZC. So this is called as a characteristic impedance. We have termed it as characteristic impedance, and we can call ZC like root of small z by small y. It can be written as root of small z by small y, right? Small z by small y. So let us discuss a little about this characteristic impedance particularly. So after that, we will move into the lossless line. Somebody is complaining about echo. Is it not clear now? Voice. Somebody saying clear? Yeah. Many people are saying that it's clear voice. Yeah. Okay. So let's continue with ZC a little bit. We have not discussed many things about ZC in the previous class, so-called long transmission line discussion. Now let's say ZC. First of all, what is that Z and Y? Z is per kilometer series impedance. Y is a per kilometer shunt admittance. Where small z per kilometer series impedance. R plus j omega L ohm per kilometer. So this Y is G plus j omega C mho per kilometer. G plus j omega C mho per kilometer. Yeah. So now if you move it the ZC here, root of small z by small y, na? So it is R plus j omega L by G plus j omega C. Just have a look this. Have a look at this one. R plus j omega L by G plus j omega C under root. Yeah. So see, numerator it's a complex number for me, and denominator is also a complex number, right? Numerator is a complex number, denominator is also a complex number. Ratio will come as a complex number definitely. Ratio will come as a complex number definitely. Okay. So after getting the ratio as a complex number, you apply square root for it. Apply square root. After applying the square root, we used to get this like some magnitude mod ZC at an angle of minus theta. We are going to get negative angle here. That's what my interest is to tell you. My interest is to tell you here, I'm going to get some sort of negative angle. Why? In the sense, it depends upon the angle of the numerator as well as the angle of the denominator. Let me think. What is the angle of numerator here? What's the angle of numerator? Tan inverse of omega L by resistance. And what's the angle of denominator here? Tan inverse of omega C by G. Tan inverse of omega L by R and then tan inverse of omega C by G. Okay. Listen please. See, actually, if you think about practical transmission lines, how is the value of G? How is the value of G? Very low, or you can say negligibly small. Yes or no? G will be negligibly small. If the G value was negligibly small, this omega C by G comes to be very large number. Omega C by G number will come to be very large number. Then tan inverse of that number, if you take tan inverse of that number, this value will be very close to 90 degrees. This denominator angle will be very close to 90 degrees, we can say. Then how is this numerator angle? How will be that numerator angle? This resistance can't be zero. Resistance can't be zero, and omega L by R tan inverse, if you calculate, it will be definitely less than 90 degrees. So numerator angle will be less than 90 degrees. Denominator angle will be very close to 90 degrees. We are getting very close to 90 degrees. Okay. Very close to 90 degrees. By that way, definitely the resultant angle of this ratio will be numerator angle minus denominator angle. Numerator angle minus denominator angle, and that resultant angle will come to be negative. Resultant angle come to be negative. Okay, for example, if I have one term like square root of 1200 at an angle of minus 20 degrees, like that, if you have some number, whatever it is, square root of 1200 at an angle minus 20 degrees. How to write it? How to calculate that square root? Means we should take the square root of the magnitude and we have to take up the angle by 2. Square root of magnitude we should take and we have to take up the angle by 2. This is a way of calculating square root of a complex number. This is a way of calculating the square root of a complex number. Root 1200 and angle will be minus 20 degree by 2. See, my intention is to tell you, this resultant angle after calculating square root will be negative only. Resultant angle after calculating the square root will be negative. Yeah. Okay. See, if the resultant angle is negative for the impedance, it's an impedance, right? Impedance. What is the nature of that impedance? What is the nature of that impedance? Anybody please tell me. Is it resistive, inductive, capacitive? Which nature? Which nature we can say for that impedance? Is it resistive in nature, inductive, or capacitive? It will be capacitive. We have a negative angle, na? So if you take up that expansion, you may get like R minus Jx, R minus Jx. So you get the negative reactance there. Negative reactance in the sense, it will be in capacitive nature. Zc is in capacitive nature. Capacitive nature. Okay. See, I'm not saying all these things for lossless line here. Strictly speaking, it's not for lossless line. For a you say for a practical transmission line. For a practical transmission line, characteristic impedance is in capacitive nature. Capacitive nature. So I'll write that in the next slide. For practical line. Practical line. Or you can say in bracket lossy line. Lossy line. Or you can say this line has attenuated line. Attenuated line. Or you can say the resistance value and conductance values are non-zero. Resistance and shunt conductance values are non-zero. For this line we are talking. For this line. Okay. So Zc is capacitive in nature. Characteristic impedance is capacitive in nature. Capacitive in nature. Capacitive in nature. Okay? Yeah. Tell me please. Zc is capacitive in nature. Zc is capacitive in nature. What's the reason for this capacitive nature? That's the question. Why it is coming as capacitive nature? Anybody please tell me? Why this is coming in capacitive nature? Because of the reason omega L by R number. Omega L by R number is less compared to omega C by G. Or omega C by G is greater compared to omega L by R. Any statement you can say. Okay. So reason for this is omega L by R is less compared to omega C by G. Omega L by R less compared to omega C by G. And if by calculating that omega and omega, you will get L by R is less than C by G is a condition or is a reason. L by R is less than C by G. Okay, all of you know this. Listen please. All of you know this. For a practical transmission line, we have a series branch and we have a shunt branch. Series branch and shunt branch. Series branch is consisting RL. Series branch is consisting RL. Shunt branch is consisting CG. Let me show that only one section. Look here, please. So this is one section I am showing. One section. So like that we have many sections now. Let me show those many sections also for you for your understanding. Right. So these are many sections I'm going to show for you. Like this, you can say RLCG. Yeah, you please listen. Please listen here. See, what is the time constant of series branch? Anybody tell me please? L by R. Time constant of the series branch is L by R. Okay. What is the time constant of shunt branch? Shunt branch is the RC circuit. R into C is a time constant. R we can write as 1 by G. So it will come to be C by G. Means you can say here, series branch time constant will be less compared to shunt branch time constant. Series branch time constant will be less compared to shunt branch time constant. This is the reason why we are saying the characteristic impedance is coming in the capacitive nature. Series branch time constant will be less compared to shunt branch time constant. Okay, listen please. Actually, energy, or you can say power, whatever it is. It is getting transmitted from one place to other place on the transmission line. Well, energy is going to be transmitted from one place to other place on the transmission line. Well, yes, sir. How it is going to be transmitted? Energy, how it is going to be transmitted means continuously, the magnetic energy will be converted into electric energy, and then electric energy converted into magnetic energy, and again magnetic energy converted into electric energy. By that way, that energy is going to be pushed, or energy is going to be propagated towards the receiving end side of the transmission line. All of you getting my words? All of you getting my words? Just check this one. Check this one. What I am saying. Energy or power is going to be propagated on the transmission line or on the wire due to the exchange of electric energy to magnetic energy to electric energy continuously. Okay, so that see, the series branch will be storing some energy first. Look here, please. The series branch will be storing some energy first. That energy will be discharged to the shunt branch, right? So the shunt branch will be storing some energy. This energy will be discharged to the next series branch. Okay, that stored energy will be discharged to the next shunt branch. That energy will be discharged to the next series branch. Like that, the energy is going to be propagated towards the end of the transmission line. Okay, listen please. Listen please. What is this time constant is indicating for you actually? What is that? Time constant is indicating for you. It is going to tell you an information regarding charging and discharging times. Time constant, whatever we have shown there, it's going to tell you some information about the charging and discharging times. Yes or no? Yes or no? So now the voice is okay. Please tell me, Samad. Is it clear now? Voice. Is there any echo now in this position? In this position, do you have any echo? Please kindly tell me. Samad, Abdul Samad. Is it clear now in this position? Yeah, so let's continue. It's saying there is no echo. Naveen Sai, Mangesh. Yeah, okay, let's continue. Let's continue now. Listen. See, if these two time constants are becoming unequal, look here, series branch time constant, shunt branch time constant. If these two time constants are becoming unequal, then definitely there is a difference in the charging and discharging of the series branch and the shunt branch. Charging and discharging of the series branch and the shunt branch. Because of the difference, definitely some distortion will be introduced in the sinusoidal wave, whatever it is propagating on the transmission line. Distortion will be introduced in the sinusoidal wave, which is propagating on the transmission line. Okay, say for example, if this is a sinusoidal wave which is propagating on the transmission line, something like this, sinusoidal wave, and because of this inequality in the time constants, we do experience some change in the wave shape. This is going to be called as distortion. That's going to be called as distortion. Okay, right? So if the series branch time constant is not equals to shunt branch time constant, then there exists a distortion in the wave propagation. Wave in the sense sinusoidal wave. Distortion in the wave propagation. Clear? Next thing. Say in the reverse wave you talk, if these two time constants are exactly equal, series branch and shunt branch time constants are exactly equal, then definitely we don't expect any distortion in the wave. We don't expect any distortion in the wave. That type of line, we are going to name it as distortion-less transmission line. Distortion-less transmission line. Okay. Series branch time constant equals to shunt branch time constant, or let me expand it. L by R equals to C by G, or you can say RC equal to LG. Then there is no distortion. There is no distortion in wave during propagation. Okay. And the line is going to be called as distortion-less transmission line. Distortion-less transmission line. The line is going to be called as distortion-less transmission line. Distortion-less line. Okay. Yeah, all these things, whatever we are discussing here, we are discussing with respect to practical transmission line only, not lossless, not the lossless line. For lossless line, how it is going to happen, we have to look. We have to look for that. Yeah. Please complete it quickly. Please complete it quickly. This is a distortion. Yeah. So let's continue like this now. Let's look. These are the ABCD and gamma. And Z is a series impedance per kilometer, R plus J omega L. Y is a shunt admittance per kilometer, you have G plus J omega S. And what do you mean by lossless line simply? Lossless long transmission line is nothing but having resistance value, series resistance value, and shunt conductance values exactly zero. Means R and G values will be zero. R and G values will be zero. So wave is nothing but sinusoidal wave. Yeah, Bala Vignesh, that is the impedance what we are talking. If you have a negative angle for the impedance, it will be expanded like R minus JX, right? R minus JX. If you have a negative reactance, it will be capacitive nature. Okay, that's not current. Always you should not say if you have a negative angle, it's inductive. You should think what is that given? Is it current or impedance? Yeah. Next thing. So let's continue. For a lossless line, R and G values will be zero. Then we have a change in the small z and small y. Accordingly, there will be a change in the propagation constant, and we have a change in the characteristic impedance of the line also. Okay, let's write first. For lossless line, we know here lossless line. Resistance value was 0. Conductance value is also 0. Now, you can write small z, it will be converted into J omega L ohm per kilometer. Small y, J omega C mho per kilometer. Small z, J omega L ohm per kilometer. And small y, J omega C mho per kilometers. Next thing. First, let's take propagation constant for the lossless line. Means gamma for lossless line. Gamma for the lossless line. Okay. You see, gamma already we said it is root of Z into Y. Z into Y. So you can get here root of Z, J omega L, Y. It is J omega C. Root of Z into Y in the sense J omega L. Why R is 0? Again, the same question you are asking me. Lossless transmission line, I said, no, there is no real power loss in the line. There is no real power loss, means there is no existence for the power dissipating element in the circuit. So, no series resistance, no shunt admittance. Okay, let's continue. See, it is J omega L into J omega C. It will be converted into a term like J omega root LC. It will be converted to J omega root LC. J omega root LC. Can anybody tell what's the units of gamma? What's the units of gamma? Gamma units will be per kilometer, right? Gamma units will be per kilometer. Very simple. Z, ohm per kilometer. Y, mho per kilometer. Ohm per kilometer, mho per kilometer. Ohm and mho gets cancelled out. And 1 by kilometer square under root. It will be 1 by kilometer. So gamma, it will be in per kilometer manner. Per kilometer manner. Okay. Now you know already gamma is equals to alpha plus j beta. Gamma equals to alpha plus j beta. Now we have found that gamma like j omega root LC only. Means what is alpha here? What is alpha? 0. And what is beta? Omega root LC. Alpha is equals to 0. Beta equals to omega root LC for the lossless transmission line. Okay. So I can say in the next slide, for this lossless line, alpha is equal to 0 and beta will come to be omega root LC. Alpha equal to 0 in the sense, alpha equals 0 in the sense, there is no attenuation. There is no attenuation in the forward moving wave or in the moving wave. In the moving wave on the transmission line, wave in the sense sinusoidal wave. Wave in the sense it is sinusoidal wave. There is no attenuation, right? So no attenuation, no attenuation in the moving wave. The forward moving wave, you can say better. Forward moving wave. Okay. See, beta omega root LC, it will be in radian by kilometer. So there is a phase displacement. There is a phase displacement. There is a phase displacement. Beta equals to omega root LC. Okay, this is about gamma briefly for lossless line. We'll recall these terms wherever it is necessary. Further, let's take up ZC for lossless line quickly. Characteristic impedance of lossless line. ZC of lossless line. ZC of lossless line. So I can write now ZC is equal to square root of Z by Y. Z in the sense 0 plus j omega L, Y in the sense 0 plus j omega C. And you observe now that j omega will be cancelled out. J omega will be cancelled out. And it will be resulting into a term like root of L by C. It will be resulting into a term like root of L by C. Root of L by C. ZC is equals to root of L by C. Okay. So all of you listen to me, please. All of you listen to me, please. We'll substitute the inductance value for the line. And we'll substitute the capacitance value for the line. Inductance value, capacitance value, we'll substitute here. After substituting these two values, we'll get a square root and we'll get some number. All of you listen. We'll get some number. What will be the angle of that number? What is the angle of that number? Is there any imaginary part in this impedance? Is there any imaginary part in this impedance? Yes or no? No imaginary part. See, if we don't have any imaginary part, and moreover, it is an impedance, right? Impedance means what's the nature of this one? What's the nature of this one? It will be resistive in nature. Resistive in nature. So, characteristic impedance of a lossless line. Characteristic impedance of a lossless line is in resistive nature. Resistive nature. This we are going to call generally as surge impedance of the transmission line. Surge impedance of the transmission line. Okay. So, characteristic impedance of a lossless line. Characteristic impedance of a lossless line itself is going to be called as surge impedance. Yeah. ZC, characteristic impedance. Better I will write the complete word. Okay. So, characteristic impedance of lossless line is called as surge impedance. Surge impedance. Characteristic impedance of a lossless line is going to be called as surge impedance. Yeah, done. Next thing. So let's say in the next slide. I'll tell you what is the meaning of surge impedance here. Kindly understand. Look at, for example, this is one transmission line. This is one transmission line with some series impedance Z as well as shunt impedance Y. All of you listen. Stop writing. Stop writing. Just listen here. How it is resistive means it is an impedance and there is no angle. It's an impedance. ZC is an impedance. You are getting root of L by C. Is there any angle for that impedance? No. Zero angle for the impedance means what is the nature of that? Resistive. Okay. It's in resistive nature, but it's not going to create any power loss. ZC is in resistive nature, but it won't create any power loss because that resistive nature is coming due to the inductance and the capacitance, not because of the resistance of transmission line wire. Okay, so you write that statement here: resistive nature, but it won't create any loss. It won't create any loss in the transmission. It won't create any loss. Yeah, all of you kindly listen. Kindly listen here what I am saying you. Don't confuse. Don't confuse. Kindly listen. See, we have some surge attack. Surge. Maybe it's a switching surge, lightning surge, whatever it may be. Doesn't matter. Surge. Surge is nothing but transient. Surge is nothing but, we said it's a transient attack. Okay. See, whenever the surge is getting attacked, how is the operating frequency, we can say? How is the operating frequency? Very, very high. So surge frequency is very, very high. That's what the term I am going to call here. Surge frequency is very high. Surge frequency is very, very high, we can say. Okay. See, whenever the surge frequency is a very, very high number, and if you are about to calculate the characteristic impedance, you can write the characteristic impedance ZC like R plus j omega L in the numerator by G plus j omega C in the denominator. Characteristic impedance. Characteristic impedance is R plus j omega L by G plus j omega C. Simple words. As the surge frequency is very, very high in number, omega L very, very high compared to resistance value, definitely. Omega C also very, very high compared to G value, definitely. Because frequency is very high, omega is very large for me. So omega into L very large compared to R. Omega C is very, very high compared to G. Means this you can write approximately as square root j omega L by j omega C, and it will be like root of L by C only. Na? It will be like root of L by C only. Root of L by C. All of you getting my words? All of you getting my words, what I am saying? See, during that surge condition, all of you listen. During that surge condition, whatever the characteristic impedance we have, that is converted into a term like root of L by C, and this root of L by C is nothing but characteristic impedance during surge operation. Hence, the name is given as surge impedance. Yeah. Please kindly relate these things. Same formula, same number, root of L by C. Same formula, or you can say same number, root of L by C. We are getting under steady state operation also. When, in the sense, by saying that resistance and shunt conductance values as 0, means particularly for lossless line, that ZC is becoming root of L by C. The same term is nothing but the surge impedance what we have defined earlier. Hence, this root of L by C, even though we say under steady state, still it is going to be termed as surge impedance. But we are not discussing about the transient operation. We are discussing about the steady state operation only. I don't know whether you have understood or not. Capacitance is not high, Satish. I said omega C is high. Frequency is very high. Frequency is very high means omega c very high compared to G. But it's a transient, no? Transient frequencies will be generally higher orders. Those are impulse signals or uneven waveforms. Uneven waveforms will have very high frequencies. Yeah, all of you understood this? All of you understood this? Please kindly respond. Yeah, good. Yeah, so I'm saying you in simple steps again. In simple steps again. Whoever is not clear, just listen. Just listen. For a lossless line, under steady state operation, lossless line. I calculated ZC. I get root of L by C. Stop there. Next, surge operation I'm taking. During surge operation, frequency is very high. Omega L very high compared to R. Omega C very high compared to G. This ZC is turning out to be an equation like root of L by C. ZC is turning out to be an equation like root of L by C. This is going to be called as surge impedance. Why? In the sense, ZC we are calculating under surge operation. During surge operation, we are calculating it. So we are naming this as surge impedance. But you see, same formula root of L by C, same formula root of L by C, I am getting even under steady state operation also. Even under steady state operation also, particularly for a lossless line. That's why I'm not changing the name. I'm not changing the name for the root of L by C. I will be calling this as surge impedance only. I will be calling that as surge impedance only. But still, we are discussing in the steady state operation of the system. Steady state operation of the system. Okay, so let's continue. Let's continue now. So I will be giving some range for this ZC for practical applications. Maybe if you think about practical transmission lines, right? Or transmission lines. Range of ZC will be generally in between 200 ohms to 500 ohms. 200 ohms to 500 ohms is a general range for that ZC. For a single circuit line, ZC will be typically 400 ohms. Typically 400 ohms for a single circuit line. For single circuit lines, typically ZC will be equals to 400 ohms. Whereas for the double circuit lines, this number will be like 250 ohms. For the double circuit lines, typically ZC will be around 250 ohms. 250 ohms. Double circuit lines. Maybe it's a 220 kV double circuit line or 400 kV double circuit line, anything. But anyhow, in the examination, definitely they used to give how much is a surge impedance. They are giving a problem, definitely they will give the surge impedance. But why we are discussing about these things means just to get an understanding. Maybe in some interview, the people used to ask you, how will be the surge impedance of a double circuit line, or how will be what you call surge impedance of a single circuit line? To get some answer for that, we are discussing about these things. I think all of you know about single circuit line and double circuit line. We discussed long back in inductance and capacitance calculations. Yeah, all of you. I need your response, please. I think all of you know about single circuit lines and double circuit lines. Yes, good. Whoever is having a doubt, just go back and check the previous classes once. Very simple. Next week. Let's discuss about the underground cables. For the underground cables, or you can say this as insulated cables. Underground cables, or you can say this as insulated cables. Yeah, please listen. For these insulated cables, how are the values of L and C? Compared to overhead line? Compared to overhead line, how will be the values of L and C? Just observe as an understanding. Just tell me. See, in case of cables, just I will tell in a simple words. Listen. In case of cables, distance between the conductors will be negligibly small. Distance between the conductors will be negligibly small. If that's the case, GMD is a very low number, I can say. GMD is a very low number. If the GMD is a very low number, inductance will be very low, na? Inductance value will be very low. Inductance value will be very low. Not only that, capacitance value will be very high. Inductance is low. Capacitance is also high. So in that situation, if you calculate that surge impedance ZC, you know it is root of L by C. L is high and C is low. Then L is low, C is high. Reverse. L is a low value, C is a high value, and ZC will be very low, I can say. ZC will be very, very low, we can say. Yeah, ZC will be very, very low. So in my view, cables will have very low surge impedance in comparison with the overhead transmission lines. Cables will be having very low surge impedance in comparison with the overhead transmission lines. So range of ZC for cables, it will be in the range of 40 ohms to 80 ohms. 40 to 80 ohms, we can say a range of ZC for cables. Whereas typical value of ZC for cables will be around 40 ohms, you can say. Typically ZC of cables will be around 40 ohms. ZC of cables will be around 40 ohms. Yeah. So I think all of you getting this. So this is regarding the surge impedance we have discussed till now. What I do in the next step is we have taken ABCD parameters of long transmission line. In those ABCD parameters, we will make these changes with respect to lossless line. So I'll take a small heading here inside this, like ABCD parameters of lossless line. ABCD parameters of lossless line. Simple, very simple thing. Just listen kindly. I will copy the same ABCD parameters which we have written earlier. This one I am copying. Okay. Yeah. See this. See the changes how I am going to make further. Look, please. Look here. Stop writing, all of you. Stop writing. Just listen. What is gamma? What is this gamma? For lossless line, particularly alpha is 0, gamma will come to be J beta. I'll keep that as J beta. That's where beta is omega root LC, phase constant. Where beta equal to omega root LC, phase constant. Next thing. Whatever the ZC we have here, ZC is characteristic impedance, strictly speaking, characteristic impedance. But I'm not going to change the notation. Notation I will take as it is, ZC only. But keep this thing in mind that ZC will be equal to root of L by C. Keep this thing in mind. ZC will be equal to root of L by C, which is in resistive nature. I'm not changing the notation for characteristic impedance and surge impedance. Okay. Yeah. Listen. See this gamma L we have na? Gamma L. That gamma L I will be replacing with J beta L in all. Gamma L I am replacing with J beta L. Gamma L I am replacing J beta L. ZC will keep as it is. That will be root of Z by C only na. So root of L by C. So I will keep the ZC as it is. Yeah. So I think all of you getting this? All of you getting this one? So if you have done, I will be asking one very simple question to you. What will be cos h of j beta L? What will be the cos h of j beta L? Generally, if you have a term like cos h of jx, in hyperbolic functions, you can write it as cos x. Cos h of jx in hyperbolic functions, you can write it as cos x. Sin h of jx, if you have that, you can write it as j sin x. J sin x. I think all of you getting what I am saying you. So cos h of j beta L, I will write simply cos beta L here. Sin h of j beta L, I will write j sin beta L. Here also you get j sin beta L. Here also, here you get cos beta. Cos beta L. Cos beta L. Clear? So let's make that replacement in the next slide for this ABCD. So you can get sending end and sending end voltage and currents will be equal to cos h of j beta L, means you write this one cos beta L, j zc sin beta L, and you have j 1 by zc sin beta L, and we have here cos beta L. Cos beta L. So this multiplied with the receiving end side quantities VR and IR. That multiplied with receiving end side quantities, you can say VR and IR. VR and IR. Yeah. Have you completed this? Any observation to be made from this ABCD now? These are the ABCD of lossless line, which is very important, and you have to remember it. Very important, and you have to remember these things. Okay, ABCD of lossless line. Lossless log transmission line. I'm asking one a very simple question. Any observation to be made here? Any observation to be made? Of course, A equals to D and AD minus BC equals to 1. Okay, A equals to D and AD minus BC equals to 1. That will happen anyhow. Any other new thing we can observe here means listen. Cos beta L we have na. Cos beta L. Beta L is some angle, some number, some angle you could say. Cosine of that angle will give some number. What is angle of this number? What is the angle of this number? Anybody tell me please? Cos beta L, what is the angle? 0 degree, right? Cos beta L some angle that will substitute there. Cosine of some angle you will have. That will be a number. What is the angle of that number? 0 degree. 0 degree. Means the angles of A and D, 0 degree. Whereas for B and C, we have J symbol, J symbol here. That J symbol will give 90-degree angle for parameter B as well as parameter C, we can say. Right. So I can write for lossless line. The angles of A and D, parameters A and D are 0 degrees. And whereas the angles of B and C are 90 degrees. B and C are 90 degrees. Angles of A and D, 0 degree, B and C will be 90 degrees, we can say. 90 degree, we can say. I think all of you clear about this? Next. So let's continue. Let's continue like this now. Let's take the VS equation here. Sending and voltage equation I'm taking them, which is cos beta L into VR plus JZC sin beta L into IR. Okay, let me write. Next slide I'm taking up. Sending and voltage equation VS equals to cos beta L into VR plus JZC sin beta L into IR. Cos beta L into VR plus JZC sin beta L into IR. Like that we are getting that equation VS, sending and voltage equation VS. One very simple question. Very simple question here. Just concentrate here. I want to make this sending end voltage and receiving end voltage exactly equal, including the angle. I will say, including the angle, I should make simply Vs equals to VR. How I can make? How I can make that Vs and VR values as exactly equal? Please tell me. Please tell me how to make that Vs and VR values as equal. See, listen now. See, for example, if you make this cos beta L value 1, cos beta L value 1, if you make, so this will come 1, okay, and sin beta L will be 0, na? Sin beta L will be 0, so 0 into IR, this number will be 0. This whole number will be 0, and you will get this number 1 into VR, so you will get Vs equals to VR. So cos beta L equals to 1 is a condition. Cos beta L is equals to 1 is a condition. Okay, please listen. Cos beta L equal to 1 means, what is beta L? What is beta L? Beta L will be 0. Okay, very good. Beta L equal to 0, then length of transmission line is 0, then there is no meaning of saying there is a line. Length of line is 0 means definitely sending end side, receiving end side are same, na? Yes or no? There is no transmission line at all if length is 0. Okay. Other than this, any other option? Tell me please. Any other option? 2 pi, 360 degree, 2 pi. So if it is 2 pi, then how much is the length of transmission line here? Means it is 2 pi by beta is the length of the transmission line. How much is the length of transmission line we have? That will be 2 pi by beta. 2 pi by beta. So I'm saying this statement, actually this statement you have to get as a conclusion, strictly speaking. You have to get this statement as a conclusion. Just listen to this one. My aim is to make Vs equals to VR, so that I have to make cos beta L as 1. So beta L is 2 pi I am saying. So length of line equals to 2 pi by beta. The meaning of this is, if length of transmission line is equal to 2 pi by beta, if length of transmission line is equal to 2 pi by beta, then you will get that Vs and VR values as exactly equal. For what length of transmission line it is happening means 2 pi by beta, this we are going to name it as wavelength. That we are going to make it as wavelength of the transmission line. Okay, so all of you getting this word? Wavelength of transmission line. That's our next heading to be chosen. Wavelength of transmission line. Generally, we will indicate this wavelength with a letter lambda. We'll be indicating that with a letter lambda. Okay. Next. Listen here. So I will be defining the wavelength like this now. It is a physical length of transmission line L. Physical length of transmission line required to have VR equals to Vs as well as IR equals to Is. Both will happen. Okay. So lambda is the physical length of transmission line. Is the physical length of transmission line at which receiving end side and sending end side quantities as equal currents as well as voltages. VR equals to Vs as well as you can get IR equals to Is. Okay, next thing. See, I will be taking up some definition from basics of physics. Tell me please, from basics of physics, how you can define this lambda? Wavelength. Wavelength means generally in a particular way, it's a distance between two crests, or you can say distance between two troughs. Or you can say distance between two troughs. Okay. else in other way, it is a period. It is a period above which the wave is going to be repeated. It's a period above which the wave is going to be repeated. But the period you have to measure in the form of length. Maybe in meters or kilometers, you have to measure that. Okay. So I will be showing that in the next statement. Wavelength is the period in bracket you write measured in meters or kilometers at which the wave repetition occurs. At which the wave repetition occurs. At which the wave is going to be repeated, else you can say wave repetition occurs. Yeah. Next. Listen, please. I will discuss little about that wave repetition, then I will recall the formula for lambda, which is nothing but 2 pi by beta. Already we have written. Okay. Yeah. See, for example, we have one lossless long transmission line here. Lossless long transmission line. Let's have a look. Lossless long transmission line. And this place, we are keeping one AC voltage source. We can say AC voltage source. And the switch is going to be closed at time t equals to 0 plus. Switch is going to be closed at time t equals to 0 plus. Observe here whatever I'm saying. Don't question it. Just look what I'm saying. We have a lossless long transmission line first. Lossless long transmission line. We kept a AC voltage source, which is going to be attacked onto the line at time t equals to 0 plus. And this is a point of analysis starting. This is a point of analysis starting. So I will say x equals to 0 here. And this may be of x equals to 1 kilometer. And towards the end of the line, I can say x equals to L kilometers. X equal to 0, x equal to 1, and then towards the end, we can say x equals to L kilometers. L. Okay, listen all of you, listen. See, at this point of x equals to 0, I will be taking up that voltage as a reference. Mod V at an angle 0. I'm taking the voltage as mod V at an angle 0. Mod V at an angle 0. Stop writing, all of you. Stop writing. Just answer to the question what I am asking. Answer to the question. Just now we have switched this voltage. Just now we have kept that voltage onto the transmission line. That voltage itself I am taking as a reference. So I said mod V at an angle 0. So this voltage wave is propagating on the transmission line. Voltage wave is propagating on the transmission line. Definitely, it will take some time to reach x equals to 1 kilometer. It will take definitely some amount of time to reach x equals to 1 kilometer. Yes or no? Yes or no? Yes or no? Yes, fine. Now, even after reaching to 1 kilometer length, magnitude of the voltage will be same because it's a lossless line. There is no attenuation. There is no change in the wave magnitude. So I would say magnitude of the voltage will be as it is mod V. But how is the angle of this one? That's the question. How will be the angle? It is getting delayed or advanced. Whether that voltage wave, is it getting delayed or is it going to be advanced? Tell me please. It will be definitely delayed. It will be definitely delayed. Why in the sense? It is taking some time to reach that point. It is taking some time to reach that point. So definitely it will be delayed. Delayed by how much angle? Delayed by how much angle means beta. That's the definition of beta actually. What's the beta we said? Phase constant, right? which is going to tell about phase shift. It's going to tell about phase shift in the wave which is propagating on the transmission line from one point to other point. So we will be getting a phase shift of beta. We will be getting a phase shift of beta, and that is delayed in the sense I have to call it is minus beta. I call it as minus beta. So beta units are what? What are the units of beta? Anybody? What are the units of beta? That will be radian by kilometer. Na? Radian by kilometer. So if the wave is traveling 1 kilometer length, it will be shifted by beta. If it is traveled by 5 kilometers, 5 kilometers means 5 beta. 5 kilometers means it will be 5 beta. So I can say it is mod b at an angle minus 5 beta, and length of transmission line at this point is x equals to 5. X equals to 5. And at the end, this point, and this will be mod b, and angle will be minus beta L. Angle will be minus beta L, we can say. Minus beta L. Okay. So to get a clear, even more clear understanding, I will be showing the sinusoidal waveforms here. I'll show the sinusoidal waveforms. Kindly observe. This point, x equals to 0 point, I'm going to show first. X equals to 0 point. So this is a voltage axis, you can say, and it's a time axis. Time axis. Just have a look here. Have a look here. X equals to 0 point waveform, voltage waveform will be like this. It is a x equals to 0 wave. X equals to 0 wave. Okay? Equals 0. At x equals to 1 kilometer, how is the wave? X equals to 1 kilometer, it will be shifted by an angle of beta. Na? So I will show it. I'll show that x equals to 1 kilometer. So same sort of x I'm showing here. X equal to 1 kilometer. So first I will copy this x equals to 0 wave. X equals to 0 wave I have copied. One minute, please. X equals to 0 wave I have copied. This one. X equals to 0 wave. X equals to 1 kilometer length wave. X equals to 1 kilometer length wave, it will be shifted by an angle of beta. So you will be getting that x equals to 1 kilometer, something like this. X equal to 1 kilometer length, and this is at angle gap. We can say it as beta. Okay, like that, if you go towards the end, right? Go towards the end, and as a reference, I am taking x equals to 0 wave first. X equal to 0 wave I am taking first as a reference. And x equals to L kilometer length wave with a shift of beta L, I might be getting something like this. Okay, so this is x equals to L length, and this angle is beta L. That angle we are going to call it as beta L. Beta L. Why can't we have phase shift if the length of the line is less than wavelength? I'm showing here, no? Yeah, listen. For example, if beta L is equals to, just look this. If beta L, or if the length of line equals to wavelength, if length of the line equals to wavelength, then how much is that beta L shift you can get now? 2 pi. You are going to get that shift as 2 pi. Now, if you show x equals to 0 wave like this, x equals to 0 wave. I will extend this x equals to 0 wave little bit more. I'm going to extend this one. X equals to 0 wave. Yeah, just have a look here. This is the x equals to 0 wave. We are extending. Okay, it's x equals to 0 wave extended. And how is it x equals to L wave now? Anybody please tell me? Tell me please. Tell me please. Beta is negative. That's what I have shown delay. Delay in the that waveform. Tell me please. How is that now? How is that? Shift here. It will be shifted by an angle of 2 pi. Na? It will be shifted by an angle of 2 pi. So you are going to get that x equals to L wave, something like this, right? X equals to L wave, we are going to get something like this. That's the meaning of the wave repetition. That's the meaning of the wave repetition. Okay, understanding? The same wave is going to be repeated. Same wave is going to be repeated at how much length? At how much length? 2 pi by beta. 2 pi by beta. That we are going to name as wavelength. That we are going to name as wavelength of the transmission line. Wavelength of transmission line. That's the meaning of wave repetition. What we have written. Wave repetition. Wave repetition. I think all of you getting some understanding about the wavelength, what I am talking exactly. Wavelength. So I'll show in the next slide the formula for the wavelength, what we have discussed till now. Wavelength of transmission line is lambda is equals to 2 pi by beta. Lambda is equal to 2 pi by beta. 2 pi by beta. No, it's not the thing, Vishnu. Why you are saying about that statement here? Sir, so all circuits we deal with in general as L equals to pi by beta. See, length is different, wavelength is different. Length is different. Physical length of line is different. Wavelength is different. If the physical length of line is matching with wavelength, then you have a in phase. That's the meaning. Okay, I will ask you one very simple question here. Simple conclusions we can say here. Simple conclusions. First one. If length of the line is equals to lambda, L is equals to lambda, then obviously you know length is equals to 2 pi by beta, or you know that beta L equals to 2 pi. Beta L equals to 2 pi. What are the ABCD parameters of line? What are the ABCD parameters of this line? Anybody tell me please? What are the ABCD parameters of this line? Cos beta L, JZC sin beta L, J1 by ZC sin beta L, cos beta L. So cos beta L, cos 2 pi, 1. Sin beta L, sin 2 pi, 0. So you'll get ABCD like 1, 0, 0, 1. 1, 0, 0, 1. These are the ABCD. ABCD will be coming like 1, 0, 0, 1. Clear? 1, 0, 0, 1. This one thing. And not only that, if that length is equals to wavelength, already we said receiving end and sending end voltages are exactly equal. Receiving end and sending end currents also exactly equal. Exactly. Beta is a phase shift. Beta is a phase constant we have discussed. Phase constant we discussed today only, right? Today only we discussed about it. Okay, so let's continue now. Let's continue like this. See, I will take one small problem, very, very small problem. Just look here. Just look here. A transmission line of 200 kilometers length 200 kilometers length has gamma means propagation constant 1.2 into 10 power minus 6 plus j 1.1 into 10 power minus 3 per kilometer. The ratio between physical length and wavelength of the transmission line is physical length and wavelength of transmission line is dash. The ratio between the physical length and wavelength of transmission line is dash. Simple, very simple question. Sir, when lambda equals to L, then wave repetition occurs. Yeah, correct. It's not the thing, Sivanath. You have to say in the reverse. Just look at this problem. Look at this problem first. You will get some clarity about it. All of you listen. All of you listen here. What is the physical length of transmission line? In this case, what is the physical length of transmission line given? 200 kilometers. 200 kilometers. Getting all of you? Physical length of transmission line is 200. Physical length of line is 200 L. 200 kilometers. What is wavelength of that line? What is wavelength of that line? It's not physically visible to you. Wavelength is not the term which is physically visible. It's on paper. Wavelength is on paper. Okay. What is wavelength? Lambda. What you can say wavelength formula? Wavelength formula is 2 pi by beta. Na? Wavelength formula is 2 pi by beta. All of you getting it? 2 pi by beta. It's in radian by kilometers. Sorry. It's in kilometers actually. It will come in kilometers. Wavelength will be coming in kilometers. Because beta is in radian by kilometer, 2 pi is in radian. Radian will be cancelled out. It will be in kilometer. I will show the units here also. It will be in kilometers. Next, please tell me, what is beta here? 2 pi any constant number. What is beta? What is beta? Beta is a term which is imaginary part of gamma. Beta is the imaginary part of gamma. So beta is equal to 1.1 into 10 power minus 3. It will be definitely in radian by kilometer. There is no doubt about it. It will be definitely given in radian by kilometer. You substitute that here. So 2 pi by, so it is 1.1 into 10 power minus 3. How much is this number you are getting? 5,712 approximately. 5712 kilometers. 5712 kilometers. 5712 kilometers. What's the meaning of this? 5712 kilometers. What's the meaning of that? Listen to me. Listen to me. Actually, the physical length of transmission line is 200 kilometers as we are showing now. Physical length of transmission line is 200 kilometers, what we are giving in the problem. And wavelength of transmission line is 5712 kilometers. Practically on the tower, I have only a line of 200 kilometers. Okay, if you make, look my words please. If you make the length of the transmission line is equal to 5,712 kilometers, then we can experience an equal phase. Or we can experience VR equals to VS and IR equals to IS. All of you getting my words? All of you getting clarity regarding this length and wavelength? Yeah. What is length of transmission line? Anybody tell me please? What is the length of line? We should say 200. What is length of line? Tell me, 200. What's the wavelength of line? 5712 kilometers. Wavelength is 5712. Is that 5712 is visible to you? Is that 5712 is visible to you? No, it's not visible to me. Which is visible to you? Physical length is only the visible number. Physical length only the visible number. Yeah, so I can say He is asking about ratio between the physical length to wavelength, right? So you have to take up that L is to lambda or L by lambda, whatever. So L by lambda is 200 in the numerator. Denominator, it is 5,712. Kilometer will be cancelled. How much is that? Ratio 0.035. All of you getting it? The length of line less than 5712. There is a phase shift in the waveform. Yes, Suresh, correct. Is it 0.035 or 55? 35. Okay. It will be like 0.035. This is the answer what we have to fill in that blank. Fill in that blank. Okay, next thing. At 5712 kilometers, it will repeat. Again, the phase shift will start from 0 from that point. We don't get VR equals to Vs for 200 kilometers length. Definitely there exists a phase shift between receiving an voltage and sending an voltage for a length of 200 kilometers. For a length of 200 kilometers. Okay, so let's continue now. So the next point, next topic you can say in this study, what we are going to discuss is velocity of the wave propagation. Velocity of the wave propagation. With how much velocity the wave is going to be propagated in the transmission line. Sinusoidal wave. Okay. So next heading, I am saying velocity of wave propagation. Wave propagation. The main aim of this is to know how much time the wave is going to take to reach the end of the transmission line. And okay, very simple thing. I have one formula for lambda already, 2 pi by beta. 2 pi by beta is one formula for transmission line. This is for transmission line from analysis what we have done. Next thing, from basics of physics. What's the wavelength? From basics of physics, wavelength will be velocity by frequency. It is from basics. From basics of physics, you can say wavelength is nothing but velocity by frequency. All the problems we are discussing mostly of lossless only. Anyhow, Mahinavanam, that we have taken some alpha also in that. You don't need to bother about that alpha, which is negligibly small, which is of 10 power minus 6 order. 10 power minus 6 order. Okay, listen please. These two I am going to match. By matching these two, we try to get this velocity of wave. Okay, so therefore, we can say velocity by frequency is nothing but 2 pi by beta. So you can say velocity is nothing but 2 pi f by beta. 2 pi f by beta. So you know already 2 pi f is omega, and this beta is omega root LC. Omega will be cancelled out. So velocity of the wave propagation will be 1 by root LC. Velocity of the wave propagation will be 1 by root LC. 1 by root LC, where this inductance L is in Henry per kilometers, let us say, or Henry per meter. Henry per meter intake. Henry per meter. And capacitance is in farad per meter. Henry per meter, farad per meter. So the overall units of this will turn to be meters by second. Velocity of the wave 1 by root LC, meters by second. Meters by second. Yes. Okay. So let's take for transmission line wire. What's the formula for inductance and what's the formula for capacitance? That we will substitute in this equation of velocity, and we'll try to make up that into a reduced form. So for transmission line wire, you know, inductance in per meter. Inductance in per meter. It will be, just look here, look the formula what I'm writing. Mu naught by 2 pi. Natural logarithm GMD by GM naught. mu naught by 2 pi natural logarithm GMD by GMR in terms of Henry by kilometer. What is capacitance formula? Capacitance formula 2 pi epsilon naught epsilon r by natural logarithm GMD by radius. Only radius we should take, farad by meter. 2 by epsilon naught epsilon r by ln of GMD by r, farad by meter. Farad by meter. See, already in the previous discussion of inductance calculation, we have written this like 2 into 10 power minus 7. Actually, that mu naught by 2 pi only we have written as 2 into 10 power minus 7. Mu naught by 2 pi itself we have written as 2 into 10 power minus 7. Okay, now you simply substitute this L and C in the velocity equation. Therefore, velocity of wave propagation is 1 by square root of L into C. Mu naught by 2 pi natural logarithm GMD by GMR capacitance 2 pi epsilon naught epsilon r by natural logarithm GMD by R. GMD by R. Okay. So you make these cancellations quickly. Make these cancellations quickly. So this 2 pi anyhow cancelled out. Not only that, ln of GMD by GMR value and ln of GMD by R, these two are approximately same. So I will be cancelling these terms also. Let right here. Natural logarithm GMD by GMR value. Natural logarithm GMD by GMR value will be approximately equals to natural logarithm GMD by R. These two are almost same, so that you can get this velocity of wave 1 by square root of mu naught into epsilon naught into epsilon r. Mu naught into epsilon naught into epsilon r we are going to get. That's the velocity of wave propagation. Velocity of wave propagation. Okay. Next. So I'll be taking up this formula exclusively for overhead line first and then for cables. For overhead lines, overhead lines. Epsilon r value will be 1. So epsilon r is the relative permittivity. Relative permittivity of the surrounding dielectric medium. Relative permittivity of the surrounding dielectric medium, that is air, which is having epsilon r value 1. So you can get velocity 1 by root mu naught into epsilon. That's it. So let's say for overhead line first. The next slide. For overhead lines. Overhead lines. Epsilon r is equals to 1. Epsilon r is equals to 1 for air. For surrounding dielectric medium, that is air. So then what is the velocity of wave here? 1 by root mu naught into epsilon naught. 1 by root mu naught into epsilon naught. So you substitute that mu naught and epsilon naught values here, you will get that velocity. So you'll get this like 1 by root of mu naught number. Mu naught is 4 pi into 10 power minus 7. Epsilon naught 8.854 into 10 power minus 12. Minus 12. So it's in Henry by meter, it's in farad by meter, so it will be in meters by second. That will be in meters by second. Anybody tell me this number how much? This number you may get like 2.9979 or 98 into 10 power 8 meters by second. 2.998 into 10 power 8 meters by second. Okay, so this is an exact light velocity. This number is an exact light velocity in the free space or in vacuum. It is an exact light velocity. Exact light velocity in the free space. The free space. exact light velocity in the free space, and this number I will be taking up as 3 approximately. So 3 into 10 power 8 meters by second we use to write most of the times for the simplification. Okay, so please complete this one. So I'll move with the next slide to take up that velocity. Current velocity, light velocity, same. Current velocity, light velocity, same. That's the meaning what we are saying now. So I can say here, velocity of wave is like 3 into 10 power 8 meters by second. And if you want to take that in kilometers by second, you'll get like 3 into 10 power 5 kilometers by second. Moreover, this is the velocity of wave propagation in lossless overhead transmission lines. It is for the lossless overhead transmission line only. Lossless overhead transmission line. Velocity of wave propagation for the lossless overhead transmission lines. Lossless overhead line. See, if it's a lossy line having some resistance in that, then definitely wavelength will be, velocity of wave propagation will be less than this number, less than that number. So I'm writing now for attenuated transmission line, attenuated or lossy, any name, transmission line, this velocity of wave will be like 2.7 into 10 power 5 kilometers by second to I think 2.5 is 0.5 to 2.8 approximately. 2.5 into 10 power 5 to 2.8 into 10 power 5 kilometers by. That's the range. That's the range of velocity of wave propagation if the line is consisting some loss. Line is consisting some loss. Okay. Yeah. Next. Next thing. Next for cables. For underground cables, how is the velocity of wave? For underground cables, how will be the velocity of wave? So epsilon r is greater than 1. For cables, we have a surrounding dielectric medium. The dielectric medium will have the relative permittivity greater than 1. Let me write. For underground cables, make it quick, please. For UG cables, relative permittivity is greater than 1. For surrounding dielectric medium, for the surrounding dielectric medium, epsilon r is greater than 1. Then if you go with the velocity of wave, it will be 1 by square root mu naught epsilon naught epsilon r. 1 by square root of mu naught epsilon naught epsilon r. So it will come to be 1 by root mu naught into epsilon naught by root epsilon r. 1 by root mu naught into epsilon naught by root epsilon r. So whatever the numerator we have, that I am going to call as 3 into 10 power 5 kilometers by second. Denominator you will have root epsilon r. So it will be 3 into 10 power 5 by root epsilon r in kilometer by second. That is the velocity of wave propagation in the underground cable. In the underground cable. Obviously, epsilon r is greater than 1. As epsilon r is greater than 1, definitely velocity of the wave in the cables will be less compared to velocity of the wave propagation in the overhead lines. Okay. So, velocity of wave propagation in the cables will be definitely less compared to velocity of wave propagation in the overhead lines. Velocity of wave propagation in the cables will be definitely low compared to velocity of wave propagation in the overhead transmission lines. Overhead transmission lines. Right? So I think all of you getting it? You have done till now. We have many places underground cables in the distribution system. We have it As well as some places in the transmission system also we have it. Yeah, correct, Imtiaz. Okay, fine. So next, let's continue with these uh, equations what we have discussed till now. We have taken different equations till this point. First one we have taken up the what we call phase constant equation. Then we have gone with the what we call velocity of the wave. Then sorry, wavelength. Then we have gone with the velocity of the wave. Three terms we have discussed newly. Three terms we have discussed newly. Of course, we have surge impedance also. Surge impedance. Let's have a small conclusion about these three terms. Let's have a small conclusion about these three terms. Just look here. Just look here. I'm going to tell you about the preference of usage. Preference of usage. Okay. Look here. First one. It is phase constant. Phase constant. Look all of you. Look all of you. See, if in the exam, if you want to find out the phase constant, first and foremost formula, what you should get in your mind, is beta is equal to omega root LC. That's it. It's the first preference. First preference will be omega root LC. L and C values are given, that you have to substitute. Yes, sometimes they will give series inductive reactance per kilometer, shunt capacitive susceptance per kilometer. In that case, this omega you send into the square root. It will come omega square now. Omega sent into the square root, you will get omega square. So you get omega L, omega C. It will be root of x into B. X is in ohm by kilometer. B is in mho by kilometer. X is in ohm by kilometer. B is in mho by kilometer. That's the beta. Okay, second option. I'm saying second option. See, look here. Second option. For example, sometimes they don't give the values of L and C. Then how to calculate beta? They don't give the values of L and C. Then how to calculate? You can write this like it is omega root LC, right? Omega by 1 by root LC. Omega by 1 by root LC. Nothing but omega by velocity of the wave propagation. Omega by velocity of the wave propagation. That is another equation what we can use for the phase constant. First preference omega root LC. If that is not possible to use, we have to go for omega by velocity. If they have not given omega, it is 2 pi into 50. If they have not given velocity, that is 3 into 10 power 5. You can get a number, right? Definite number you are going to get. Yeah. So this is regarding the phase constant. And second term we have discussed is wavelength. What is the first preference for wavelength? Lambda is equals to 2 pi by beta. Lambda is equal to 2 pi by beta. First preference is lambda is equals to 2 pi by beta. This is the first preference. If that is not possible to use, means if they have not given beta value in the problem, then the second preference will be velocity by frequency. Second preference will be velocity of the wave by frequency of the operation. Okay, fine. Next term. Velocity of the wave propagation. Okay, first one. Velocity of the wave equals to very basic formula 1 by root LC. Very basic formula for velocity of the wave propagation in the overhead lines is 1 by root LC. Okay, if that is not possible, if it is not possible to calculate velocity by using this L and C, if they have not given L and C, in the question, then you go with a formula for velocity like 3 into 10 power 5 by root epsilon r in terms of kilometer by second. This is another way of it. That is another way of writing. Okay, please be clear. You should use only the first preference all the time. If it is not possible, then only we should move to the second preference. Yeah. So have a break for 5 minutes. So after break, I will be continuing with this lossless long line ABCD parameters further. 5 minutes. I have resumed the audio video on screen. Resumed the audio video on screen. So let's take up the sending and voltage equation what we have written earlier. Just have a look here. See, listen. So this is the sending and voltage equation we have chosen, like Vs equals to cos beta L into Vr plus JZC sin beta L into IR. Okay. We said that our aim is to make receiving end voltage and sending end voltage as equal. The meaning of that is we are going to extract a good performance from the load. Good performance from the load by making the receiving end and sending end voltage as exactly equal. For that purpose, what you have suggested is you go with cos beta L equals to 1. Cos beta L equals to 1 means length of line required is 2 pi by beta. But if I calculate this length, listen please. If I calculate this length of line required for our 50 Hz operation, for our 50 Hz frequency of operation, it is experiencing this number as very, very high, like 5,700 kilometers we have done in one problem, 5,712 kilometers or 6,000 kilometers. Like that, we can experience that length of line required to match this Vs and Vr values as equal. But it is not practical, or it is not required actually. It's not required to run a line of that much length, 6,000 kilometers length of line. Running that much length of line is not necessary for us. So practically speaking, the length of the line may be like 100 kilometers, 150 or 200. Like that, we can experience the physical length of the transmission line wires. Following all of you. Now the question is, look here, all of you. Sending end voltage Vs is equals to cos beta L into Vr plus JZC sin beta L into IR. All of you listen please. I'm explaining the terms again. I need your response clearly. Earlier, to make that Vr equals to Vs, we said that length of the transmission line required is 2 pi by beta. But the 2 pi by beta, if I calculate for 50 Hz operation, that is coming in the order of thousands. Constructing a line of thousands of kilometers is not required. It is not practical to say. But practically speaking, how much is the length of transmission line required means maybe 100 kilometers, 200 kilometers in that range. Okay, so I have a line length, practically line length 200 kilometers. Line length is 200 kilometers, practically speaking. Operating frequency is 50 Hz. Surge impedance of transmission line is, let us say, 350 ohms. Surge impedance of transmission line is 350 ohms. These are the details of the transmission line wire. Now, listen kindly. Now, the aim is to make this Vr and Vs values as equal. At least magnitudes. Forget about angle. At least we try to make mod Vr and mod Vs values as equal here. Okay. So to make magnitude of the receiving end voltage is equals to magnitude of the sending end voltage. What I have to do? What I have to do to make receiving end voltage magnitude and sending end voltage magnitudes as equal? What we have to do? Anybody? Please tell me what we have to do for this. Nobody is responding. All of you have understood the question first. This is one place where you have to be very clear. I am saying you. All of you understood the question what I am asking you. All of you understood the question. Beta L is 0, means length of line is 0. What's the thing you are doing? Shivateja, what's you are doing? Huh? Beta L equals to pi, there is a negative. And there also length of the line is something like 3,000 kilometers. That's also thousands of kilometers. Please listen what I am saying. Length of line I have already fixed. You don't have a chance of varying length. Frequency 50 Hz. Beta is also constant. ZC 350. Surge impedance is also constant. Means my interest is to tell you cos beta L is a constant number. Constant number. ZC sin beta L also constant number. Also constant number. Now, to make that VR and VS magnitudes as equal, to make that VR and VS magnitudes as equal, we have to modify, vary the distance between the lines. Okay. Listen now, listen. Right? So to have the VS and VR magnitudes as equal, only one choice is that you have to vary the receiving and current value. You have to vary the receiving and current value. All of you getting this one? All of you getting this? Yeah. See, that receiving and current in the sense, particularly if you take up that receiving end side load, something like this. Take. So this is a receiving end side voltage, VR, and this is the receiving end side current, IR, and this load is having an impedance of ZL. Load is having an impedance of ZL. What is it receiving and current you can write from this? That is nothing but receiving and voltage by load impedance. Receiving and current is equals to receiving and voltage by load impedance, so-called ZL. Okay, so this IR, whatever we have, I am going to replace with VR by ZL. This we are going to replace VR by ZL. Simple. Now, simply you try to make the load impedance value ZL exactly equals to ZC. You try to make load impedance value exactly equals to ZC. If you do that, this ZC and ZL will be cancelled. ZC and ZL will be cancelled out. After cancelling that, what you can say? VS equals to cos beta L into VR plus J sin beta L into VR. VR is common. By taking VR common, you get cos beta L plus J sin beta L. Right? And what's the magnitude of that? 1. And obviously, you can get that magnitude of the sending end voltage and magnitude of the receiving end voltage as equal. Mod VS and mod VR values you are going to get as equal. All of you getting it? Right? So, obviously, what's the need of making VS equals to VR means to avoid the compensation. To avoid the compensation, we are making that VS equals to VR to get a good performance from the load. Yeah. So I can say here to make that mod VR equals to mod VS, I should keep the load impedance value. Exactly equals to surge impedance. I should keep the load impedance value exactly equals to surge impedance. Okay. Yeah, kindly follow this. What I am saying you, Mallesh. Load is not in our hands. Okay, that I know. How much load we have to keep to achieve it? That you think. So ZL value we have to match with ZC. So we have to keep the load impedance value exactly equals to surge impedance of transmission line. By that way, we are going to get the receiving end and sending end voltage magnitudes as equal. This type of loading, we are going to call it as surge impedance loading on the transmission line. This type of loading we are going to call it as surge impedance loading on the transmission line. That's the next topic what we are going to discuss. Yeah. So the next topic here is surge impedance loading. It's very, very important for GATE examination as well as IES also. Surge impedance loading. Shortly, we can call it as SIL. Shortly, we are going to name it as SIL. Yeah. See, sometimes the surge impedance loading can also be called as natural loading of transmission line. Right? Surge impedance loading can also be called as natural loading of the transmission line. Natural loading of transmission line. Natural loading on transmission line. Or else you can call it as ideal loading on a transmission line. Ideal loading, or you can call this as, or you can say it as ideal power transfer capacity. ideal power transfer capacity. Transfer capacity. Any name you can use. Ideal loading you can use, ideal power transfer capacity, or you can say natural loading on the transmission line. Yeah, listen first. Listen. See, this is the practical transmission line wire we have. Practical transmission line. So I'm showing two wires here. Two wires I'm showing. Right. So it's a forward wire, and I will show the return wire also. The down. Forward wire and return wire. Okay. So this side, sending end side, we will be keeping some voltage source, Vs. Receiving end side, I was interested to keep some load. Keep some load. Listen, please, listen. First of all, this line is a lossless line. Lossless line. And it's having a surge impedance of jets. Surge impedance of jets. What's the nature of ZC? Anybody? Tell me, please. What's the nature of ZC? What's the nature of ZC? Resistive. ZC is in the nature of resistive. Okay, resistive. See, the aim is to match the load impedance value equals to surge impedance. The aim is to match the load impedance value equals to surge impedance. So what is the nature of load impedance we should select out? What is the nature of load impedance we should select? That should be also resistive in nature. So that's why I will be keeping some resistive load. I will be keeping some resistive load here with a value Z. With a value Z. Fine. So I will be showing this receiving end side voltage VR and the receiving end side current as IR. Similarly, sending end side voltage Vs, sending end side current as Is. These are the notations. To match the load impedance exactly equals to surge impedance, I have taken that ZL also in the form of resistor. Okay, let's continue. Let's continue now. Some small relations I am going to take up. VR is equals to IR into ZL, else IR equals to VR by ZL. Anything. Receiving end side, VR is equals to receiving end current into load impedance. So that IR is equals to VR by ZL. IR is equals to VR by ZL. Next thing. See, from this point onwards, anywhere in the discussion, if I ask you, what is the loading on the transmission line wire? What is loading on the transmission line wire? That is nothing but the amount of the power consumed by the load. Amount of power consumed by the load kept at the receiving end side, which is VR square by ZL. VR square by ZL. That's the formula what we are going to use. Let's say loading on the transmission line. Loading on the transmission line is nothing but receiving end voltage magnitude square by load impedance. Receiving end voltage magnitude square by load impedance. This we are going to name as loading on the transmission line. VR square by ZL. VR square by ZL. So I think all of you getting this? Till now what we discussed? Now let's take the first heading. First heading here inside this. Making the load impedance. Making the load impedance value equals to surge impedance. Okay, that's the first heading I'm going to take. First heading is if the load impedance value exactly equals to surge impedance. That's the first heading. Listen carefully. ZL equals to ZC. Okay, now what is sending end voltage equation? What is it sending end voltage equation and sending end current equation? That will write, and we will keep that condition of ZL equals to ZC in that. Now, tell me please, what is sending end voltage equation? Sending end voltage Vs equals to cos beta L into VR plus JZC sin beta L into IR. Okay, it's the lossless long transmission line. Lossless long transmission line. It will be having ABCD parameters. Cos beta L, J ZC sin beta L, J1 by ZC sin beta L, cos beta L. Okay, so I can say first here. So sending end voltage is equal to cos beta L into VR plus JZC sin beta L into IR. JZC sin beta L into IR. Like this, you can say sending end voltage equation. Now, already I said you, IR is nothing but VR by ZL. You can replace. Let's continue with this now. Cos beta L into VR plus JZC sin beta L. In place of IR, I will be keeping VR by ZL. I will be keeping VR by ZL. But already, as you know, ZL and ZC are equal. ZL and ZC are equal. So I will be cancelling these two. Right? So this ZL and ZC will be cancelled. Right here, since load impedance and surge impedance are equal. After cancelling it, I will be writing this like cos beta L VR plus J sin beta L into VR. Cos beta L VR plus J sin beta L into VR. So you can take that VR common now. VR common in the next slide. Vs is equals to VR into cos beta L plus J sin beta L. J sin beta L. So if you take up this cos beta L plus J sin beta L in other form, you can write this like e power j beta L. E power j beta L equals to cos beta L plus J sin beta L. E power j beta L is equals to cos beta L plus J sin beta L, and this will come to be VR at an angle of beta L. VR at an angle of beta L. That's the sending end voltage. Sending end voltage, you will be getting like VR at an angle of beta L by using Euler's theorem. R into e power j theta. R into e power j theta can be written as R at an angle theta. R at an angle theta. Continue. Take up sending and current equation in a similar way. Try to write down the sending and current equation. Sending and current, IS. It is J1 by ZC sin beta L into VR plus cos beta L into IR. J1 by ZC sin beta L into VR plus cos beta L into IR. What is this VR? You can write that VR is nothing but IR into ZL. So in place of VR, J1 by ZC sin beta L. So in place of VR, I am keeping IR into ZL. IR into ZL. So plus cos beta L into IR. So already we said that ZL and ZC are equal. Let's cancel them. Right here, since load impedance and surge impedance values are equal, so I am cancelling them. By cancelling them, you can write the sending end current here. All these things we are doing under steady state only. Under what chapter we are discussing these things? Steady state or transient? Under what chapter we are doing all these things? Steady state, right? So all the things, whatever we are discussing is under steady state. So the sending end current you can get like J sin beta L into IR plus cos beta L into IR. So you can take that current common. By taking that current common, so you can have cos beta L plus J sin beta L. So you can get this like IR into e power j beta L, else you say IR at an angle of beta L. Sending end current, IS is equals to IR at an angle of beta L. IR at an angle of beta L. Clear? I think all of you getting this? Is it okay? Fine. Now let's think in another way. With respect to this condition of operation only. With respect to this condition of operation. So I'm taking one lossless line as an example. Just have a look. This is that lossless line what we are discussing now. Let me show the same diagram also. So this is the lossless transmission line wire. On one side you might be having voltage source as we said, and the other side we have a load. Load in the sense it's a resistive load. Resistive load, and this load impedance is ZL. Load impedance is ZL. Just follow the words. Follow the words, please. Follow the words. Follow the words, please. See, this is a sending end voltage Vs, sending end current Is. And this is a receiving end voltage VR, and then receiving end current I am showing as IR. All of you listen. All of you listen here. All of you listen here. Stop writing. Stop writing. We have four phasors here: sending end voltage currents, receiving end voltage currents. I am choosing. All of you listen. Stop writing. Receiving end voltage I am considering as a reference. Receiving end voltage I am considering as a reference mod VR at an angle 0. Mod VR at an angle 0. As a load is a resistive load. As a load is a resistive load, then obviously current IR will come with some magnitude and angle as 0 degree only. Na? As a load is a pure resistive load or UPF load, resistive or you can see UPF load, definitely receiving end current will be having angle of 0 degree as a voltage. Next thing, next. Receiving end side over. Receiving end side over. Let's move to sending end side. See, generally as a notation, we have some phase angle between sending end voltage and receiving end voltage. We have a phase angle between sending end voltage and receiving end voltage. So that is delta we have taken up earlier. So I can write the sending end voltage as mod Vs at an angle delta. Sending end voltage I am taking up as mod Vs at an angle delta. Clear? Right. Notations have you understood? I didn't take ZL equals to ZC here. I have not taken ZL equals to ZC till now. Till now I have not touched that word ZL equals to ZC. Now I am taking them. Now I am taking them. ZL equals to ZC. ZL equals to ZC. VR, I will keep mod VR at angle 0. IR, mod IR at angle 0. But you calculated Vs and Is, right? Calculated Vs and Is. What is Vs? What is Vs here? VR at an angle beta L. Look here, please. VR at an angle beta L. Actually, that VR is mod VR at an angle 0 degree, and again at an angle of beta L we have. So it will come to be mod VR at an angle of 0 degree plus beta L. So it will be beta L. VR is mod VR at an angle 0, and we have again at an angle of beta L. So this overall will come to be mod VR at an angle of beta L. That's it. So your sending end voltage will come to be mod VR at an angle of beta L. How is your sending end current with respect to this condition of ZL equals to ZC? You know it is IR at angle beta L. What is IR? We know it is mod IR at angle 0. So you can write this like mod IR at an angle 0 degree at an angle of beta L. So this will be coming like mod IR at an angle of beta L. So I can say here, this is modulus of IR at an angle of beta. Modulus of IR at an angle of beta L, you can say. So I think all of you getting these things. We expressed sending end voltage and currents in terms of receiving end properties. Receiving end voltage and currents, you can say. Okay. Now, next thing. Listen. Receiving end side. Receiving end side. What is the power factor at receiving end side? Cos pi r. Receiving end power factor is how much? Similarly, What is the sending end side power factor? Cos phi s. What is the receiving end power factor? Cosine of angle between receiving end voltage and current. Right? Cosine of angle between voltage and currents. So you can see both are having a 0-degree angle. So cos of 0 minus 0, cos 0, that will be 1. What is sending end power factor? Sending end power factor. Cosine of angle between Vs and Is. Na? Cosine of angle between Vs and Is. Vs angle, beta L. VR angle, also beta L. So it is beta L minus beta L is a phase angle gap. Cos 0, that will be 1. So receiving end power factor is unity. Sending end power factor is also unity. Receiving end power factor is 1. Sending end power factor is also 1 in this condition of ZL equals to Z. In this condition of ZL equals to Z. Okay. Further discussion. Further more things we are going to take up. This is the complex power injected to receiving end side SR. This is the complex power supplied by sending end side SS. Complex power injected to receiving end bus SR. Complex power supplied by sending end side SS. What is SR? Formula for SR? VR into IR conjugate. What is SS? VS into IS conjugate. Let's calculate them. Let's calculate. Complex powers. Complex powers. SR equals to VR into IR conjugate. VR into IR conjugate. What is VR? Mod VR at angle 0. Mod VR at angle 0. What is IR conjugate here? IR conjugate is mod IR at angle 0. Mod IR at angle 0. So it will come to be mod VR into mod IR at an angle 0 degree. Mod VR, mod IR at an angle of 0 degree. And there you get some real part and imaginary part. Real part VRIR, imaginary part 0. Real part is VRIR magnitudes, imaginary part will be 0. Imaginary part will be 0. Next step, SS, sending end side complex power. You know it is VS into IS conjugate. VS into IS conjugate. What is VS here? What is VS? Just look back. VS is mod VR at an angle beta L. Mod VR at an angle of beta L. Okay. What is IS conjugate? Mod IR at an angle minus beta L. Mod IR at an angle of minus beta L. So you can get this like mod VR into mod IR, and this resultant angle is 0 degree. Resultant angle will be 0 degree. So you can get from this like mod VR mod IR plus J0. Mod VR mod IR plus J0. J0. So any observation to be made now? Any observation to be made from this? SR and SS values are exactly equal. Yeah. SR and SS values are exactly equal. SR now? Yeah. So SR and SS values are exactly equal means the meaning is sending end side complex power and receiving end side complex power both are exactly same. Both are exactly same means whatever the line connected between them, it won't consume any complex power. It won't consume any complex power. Okay. Else you can say the line will not consume any real power as well as it won't consume any reactive power also. It won't consume any real power as well as it won't consume any reactive power also. See, actually, we said the line as a lossless line. It won't consume any real power. That's okay. It's a lossless line means it won't consume any real power. But the speciality here is it won't consume any reactive power. It won't consume any reactive power. Okay. So in this situation, let me write as SR is equals to SS. Transmission line does not consume any complex power. does not consume any complex power. Does not consume any complex power, else that implies transmission line is neither sink nor source of reactive power. I will say. Real power it won't consume anyhow. Transmission line is neither sink nor source of reactive power. Nor source of reactive power. It will be neither sink nor source of reactive power. Yeah. Next, let's think little about the transmission line reactive power. Already we discussed in line constants that I am going to recall. Just have a look here. For example, just the line is consisting series element as inductive in nature, shunt element as capacitor. Just for indication, for idea, I am showing a series inductor here. Like this. We'll show one capacitor. Okay, this is a transmission line approximate model. So inductor, it will be absorbing reactive power. Inductor will be absorbing the reactive power, and that formula will be QL absorption. Capacitor delivering reactive power, I can say it is QC supply. Inductor absorbing reactive power QL. Capacitor delivering reactive power QC. Capacitor delivering reactive power QC. Listen. What is formula for QL absorption and what's the formula for QC supply? QL absorption formula I square into XL, where I is RMS current, of course, definitely RMS current only. IRMS square into XL is a reactive power absorbed by the transmission line. What is the reactive power supplied by the transmission line? What is that reactive power supplied by the transmission line? So it will be VRMS square by XC. Voltage square by capacitive reactance. Voltage square by capacitive reactance. QL absorption, QC supply we have written. Now, based on these two, what is the net reactive power absorbed by the transmission line? What is the net reactive power absorbed by the transmission line means it is QL absorption minus QC supply we have. So let's say in the next slide, net reactive power absorbed by the transmission line is nothing but QL absorption minus QC supply. QL absorption minus QC supply. So which is IRMS square into XL minus VRMS square by X. IRMS square into XL and the other one is VRMS square by X. Like this you can do. That's the net reactive power absorbed by the transmission. Net reactive power absorbed by the transmission. But now, for the situation of ZL equals to ZC, for the situation of the load impedance equals to surge impedance, load impedance equals surge impedance, we are getting a condition that the transmission line is neither sink nor source of Q. So this value will become 0. For ZL equals to ZC condition, ZL equals to ZC condition, net reactive power absorption is equal to 0. So I can call here RMS current square into XL is equal to RMS voltage square by XC. So you can write now IRMS square into XL is omega into inductance, you can say. And here it is VRMS square into 1 by XC is omega into capacitance. Omega cancel. Omega will be cancelled out. IRMS you can write as IM by root 2. VRMS you can write it as VM by root 2. VM by root 2. So I'm showing here IM by root 2 whole square into inductance, and it is here Vm by root 2 whole square into capacitance. Means you can comment here that half L Im square means magnetic energy stored in the line will be exactly equals to the electric energy stored in the line. Half L Im square is equals to half C Vm square. Peak magnetic energy stored and peak electric energy stored, these two are exactly equal for the condition of load impedance matched with the surge impedance. Load impedance matched with the surge impedance. Half L Im square is equals to half C Vm square. Yeah. Done. Till now, we have discussed about many things by taking the ZL equals to ZC condition. By taking the ZL equals ZC, we have discussed many things here. But what is the definition of surge impedance loading? What is SIL? If anybody asks you, what is surge impedance loading? How we have to define it? How we have to define that surge impedance loading? Yeah. What is surge impedance loading? What's the definition of that? What is SIL? That's a question we have to ask. Tell me please. Tell me please. See, surge impedance loading in a single term, I will take single term. Just look here. This is some load impedance. This is some load impedance. Simple question. You have to answer this. You have to answer this. Whenever I change the load impedance value, whenever I am changing the load impedance value, whether the power consumed by the load is going to be changed or not. Whenever we are changing the load impedance value, the power consumed by the load is going to be changed or not. Tell me please. Yes, definitely. Whenever you are changing the load impedance value, power consumed by the load is also going to be changed. Now the thing is, at the situation where if we keep ZL equals to ZC, at that time, whatever the power demanded by the load you have, that we are going to call it as surge impedance loading. So simply, surge impedance loading is nothing but the amount of the power consumed by the load for a condition of ZL equals to ZC. All of you understood the meaning, right? So else it is a power supplied by the transmission line, power flow in the transmission line, amount of power flow in the transmission line, loading on the transmission line for the condition of ZL equals to ZC, right? So I can say here what is SIL means. It is the amount of power flow or loading on the transmission line, if load impedance, if the transmission line is terminated with its load impedance. Load impedance. Kindly look at this. It is the amount of the power flow or loading on the transmission line if the transmission line is terminated with its load impedance. Nothing but keeping the load impedance equals to surge impedance. Line is terminated with its surge impedance. Terminated with its surge impedance, not surge impedance. Line is terminated with its surge impedance is nothing but matching the load impedance equals to surge impedance. Matching the load impedance equals to surge impedance. Right. So I can say here, SIL is equals to I'm writing here SIL is equals to, in a short way, loading on the transmission line, by keeping load impedance equals to surge impedance. Loading on the transmission line by keeping load impedance equals to surge impedance. And what is the loading on the transmission line formula? We have this like mod VR square by ZL, and this we should get by keeping ZL equals to ZC. That we should get by keeping ZL equals to ZC. And by keeping ZL equals to ZC, what is that mod VR you can say? What is that mod VR you can say by keeping ZL equals to ZC? That will be Vs, right? That will be Ds. So in the numerator, you can write Vs square. In the denominator, you can keep this is ZC. You can keep that as ZC in the denominator. So I think all of you getting it? All of you getting it? Is it okay? Yeah, for any transmission line, these conditions are valid. For any transmission lines. Okay. So now in a general way, if you want to write the surge impedance loading, I'll say it is simply rated voltage square by surge impedance. In general, if you want to write SIL, in general, surge impedance loading per phase, first I'm writing, it will be V rated per phase square, by surge impedance. Yes. And if you want to get the SIL value in 3 phase, we have to multiply this with 3. ZC per phase only. Always surge impedance is measured in per phase manner. SIL 3 phase, if you want to have, so it will be 3 into rated voltage per phase square by surge impedance. 3 into rated voltage per phase square by surge impedance. What do you mean by 3 into rated voltage per phase square? That is nothing but rated voltage line to line square. Rated voltage line to line square by surge impedance. Rated voltage line to line square by surge impedance. It won't disappear. It will be there. That will be compensated on one another. That's the meaning. Yeah. So it's a SIL 3 phase. Next thing. So till now we have discussed about many things of saying that ZL equals to ZC. Just recall all the things. Now. ZL equals to ZC. And we are experiencing that. Look once please. We are experiencing that mod VR, mod Vs values are exactly equal. Mod IR, mod IS values also exactly equal. I want to write one more term here. Kindly accept it. You can adjust down to this. Just look here. For ZL equals to ZC condition, what we are discussing. At that load impedance matches with the surge impedance condition. We are getting mod VR and mod Vs values exactly equal, as well as mod IR and mod IS values are exactly equal, and that angular difference between voltages will be beta L. Angular difference between the voltages will be beta L. Okay. Next thing. I will ask one very simple question with respect to this. Listen. See, can we get only the magnitudes of receiving end and sending end voltage as equal? Or can I say voltage magnitude throughout the length of the line is same? Can we say only end voltages are equal? Or can I say voltage magnitude throughout the length of the line is same? In this condition of ZL equals to ZC. Only end voltages are throughout the line. Okay, for example, if you take voltage at any point X on the line, Vx. Voltage at any point X on the transmission line, Vx. What's the formula for that? Just L what we have to replace with X. That's it. L we have to replace with X. See this. Cos beta x into VR plus JZC sin beta x into IR. Into IR. See, you know already this IR you can replace with VR by ZL. And already we said ZL and ZC are equal in this condition. ZL, ZC will be cancelled out. And you can get this like VR at an angle of beta x, obviously. All of you getting this? ZL equals to ZC. ZL equals to ZC. So ZL, ZC will be cancelled out. And VR is common. Cos beta x plus J sin beta x. It will come to be VR at an angle beta x. VR at an angle beta x. What's the meaning of this now? What's the meaning of this? At x point, voltage magnitude and receiving and voltage magnitude both are equal. Currents also equal. Means my interest is to tell you, throughout the length of the line, if I measure the RMS voltage magnitude, throughout the length of the line, if I measure the RMS voltage magnitude, that will be same. That will be same. As well as current magnitude, RMS current magnitude also same throughout the length of the transmission line. If you plot this voltage profile, it looks to be a straight line. This line we are going to name as flat line. Okay, right. So I can say in this case, if mod V values are same throughout the length of the line, mod V and mod I both I will write same place. But you should not assume that mod V equals to mod I. That's what I'm saying. Mod V is not equals to mod I. Mod V is same throughout the line. Mod I is same throughout the line. Same throughout the length of the line. Without placing any extra element. In the transmission line. Then the line is going to be called as flat line. And this can also be called sometimes as infinite line. I will discuss about this in the transient analysis later. This can also be called as infinite line. Mod V, mod I values are same throughout the length of the line without keeping any extra element. Then this line is going to be called as flat line. So we experience a flat voltage profile. That's the meaning. Only phase angle is going to be changed. Only phase shift is there, but you don't have any change in the magnitude. So this behavior we are getting for a condition of ZL equals to ZC. We are getting this behavior for a condition of ZL equals to ZC. So after that, we said regarding complex powers, SR and SS values are equal. We say line is neither sick nor source of Q, and we have defined what is the circumference for X. Okay, right. Now let us discuss about the conditions like ZL less than ZC, what will happen? ZL less than ZC, what will happen? Next, ZL value greater than ZC, what will happen? These two things we will discuss, and then we will be giving some sort of conclusions. Okay, yeah. Next heading you can say load impedance value was less compared to surge impedance. Load impedance value was less compared to surge impedance. First, I'll write two terms here. One is loading on the transmission line. Next one is SIL. Can I say SIL is a constant number for a given line? SIL is a reference for the line. SIL, it's a constant value for a given line. Yes or no? It is a rated voltage square by surge impedance, right? It's a constant number. But what is the loading on the line? VR square by ZL. That value may vary. That value may vary. See, this is a SIL. Loading may vary according to the load what you are giving. According to the load what you are giving, loading may vary. Sometimes that loading may be equals to SIL. Sometimes it may be higher than SIL. Sometimes it may be lower than SIL. We have studied till now what will happen if loading is exactly equals to SIL. Loading is exactly equals to SIL. Now we are going to study what will happen if the loading is more than SIL or loading is less than SIL. That comparison we are going to study. All of you understood the point what I said? All of you understood the point? For your for further clarity, I'll tell you. Just listen. For example, I have a 765 kV line against 400 kV line. Okay. 400 kV line, 400 kV, three-phase line has a surge impedance value. I'll say it is 250 ohms. 250. Can you calculate what is SIL here? Can you calculate what is SIL? It's a lossless line. It's a lossless line. Can you calculate what is SIL? It is rated voltage line to line square by surge impedance. So it's a three-phase SIL we have done. So it's in megawatt. How much is that number? Anybody tell me this number? 640 something. You get approximately 640 megawatt. 640 megawatts. That is SIL of the transmission line. SIL of the transmission line. Now what we are going to discuss here. If the loading on that 400 kV line is more than 640 megawatt, how is the behavior? If the loading on that 400 kV line less than 640 megawatt, how is the behavior? That study we are going to do further. Okay, let's take up ZL less than ZC. ZL less than ZC. I will write both loading on the transmission line. Loading on the transmission line is receiving end voltage square by load impedance. Surge impedance loading on the transmission line is sending end voltage square by ZC. Sending end voltage square by ZC. But generally, voltage magnitudes will be more or less equal. You forget about that VR square and VS square values. Forget about the VR square and VS square values change. Okay? Yeah. So let's see first. ZL is less now. If the load impedance is decreasing, I can say loading will be increasing because loads are connected in parallel. Loads are connected in parallel. Whenever we are switching loads onto the transmission line continuously, we experience that power demand is increasing. Power demand is increasing. As the loads are connected in parallel, net impedance is decreasing. Net impedance is decreasing. Okay. Loading is increasing. Means I can say a situation here. Loading is greater than surge impedance loading. Situation here, loading greater than SIL. Loading is greater than surge impedance. I will discuss about this one a bit briefly. I am going to discuss about it. Just have a look. Simple. Very simple, very simple. If the power demand was increased, what will happen to receiving end current? If the power demand value was increased, what will happen to receiving end current? Increases. Receiving end current will be definitely increased. Okay, next. If that receiving end current is increasing, we can say that current in the transmission line also increases. Current in the transmission line also increases. Yeah, I'll write. As loading value was greater than SIL, current magnitude in transmission line increases. Transmission line will increase. Current magnitude in the transmission line increases. Not only that current increment, because of this current increment, please listen. Because of this current increment, can I say magnetic energy in the transmission line will be higher than the electric energy? Can I say that magnetic energy will be higher than the electric energy? Yes, right? That implies, or else you better say I increases in the transmission line compared to ZL equals to ZC condition. ZC condition. Comparing to that condition, I'm saying. Comparing to ZL equals to ZC condition, current is increasing. But actually, for ZL equals to ZC condition, already we mentioned that half LI square equals to half CV square. But for the present case, current is increasing compared to the previous current. So definitely half LI square will be dominating the value of CV square. So therefore, you can write half LIM square value will be greater compared to half CVM square value. Half LI square value will be greater compared to half CV square. Not only that, if you extend this further, you can say I square into XL will be more compared to V square by X. I square into XL will be more compared to V square by XC. V square by XC. Okay, then net reactive power absorbed by the transmission line. Net reactive power absorbed by the transmission line, which is nothing but I square into XL minus V square by XC. This number will be positive. I square into XL minus V square by XC, that number will be positive. So definitely transmission line is absorbing the reactive power, else you can say it is acting as sink of reactive power. Line is acting as sink of reactive power. Transmission line will act as sink of reactive power. Sink of reactive transmission line will be acting as sink of reactive power. Sink of absorbing the reactive power. Yeah. So let us take up the two-port network model of line to discuss about this thing. So I am taking the two-port network model of transmission line like this. It's ABCD. And this side you have a voltage source. We have a voltage source here. And this side we have a load. This is a ZL. Yeah, look please. Is VS and this current is IS. And it is VR IR. VR IR. Listen all of you. Simple. Just listen. First we'll talk about reactive power. ZL less than ZC and how I know. ZL less than ZC. First we'll talk about reactive power. First, this load what we have shown here. Is it absorbing any reactive power? Load, is it absorbing any reactive power? Yes or no? No, because it's a resistive load. Na? We kept a resistor, so it won't absorb any reactive power. So this Q load is zero. What about your line? Line is absorbing some reactive power. Who has to supply that reactive power to the line now? Definitely source has to supply. So we have a reactive power supply from source to line. We have a reactive power supply from the source to line. Something like that. Okay, next thing. What is the load power factor? Cos pi r value? Unity. Cos pi r value will be unity because it is a resistive load, so you can say it is 1. Now, could you please tell me, while you are defining the source power factor, is it required to consider only this load or is it required to consider the line also? While you are defining the source power factor, is it required to consider only load or line also? Definitely line also has to be taken. Line also has to be taken. See, what is the load on the source now? What is the load on the source here? That is a combination of line and load. Combination of line and load means cascade connection of this line and the ZL. Cascade connection of this line and the ZL. This whole we are going to name it as effective load on the source. This whole we are going to call it as effective load on the source. Effective load on the source. Okay. What is the nature of this effective load? What is the nature of this effective load? Is it inductive in nature or capacitive in nature? Or resistive in nature? Which nature we can say? Which nature we can say here? That will be inductive in nature because one element is absorbing reactive power. So it is inductive in nature. Inductive in nature. See, listen, very simple question. If it is inductive in nature, all of you listen here, inductive in nature. What nature of current this source should supply? Lagging current. Source should supply lagging current. Source should supply lagging current. Then, how is your source power factor? How is your source power factor? Cos phi s, which is less than 1. Cos phi s, which is less than 1. And moreover, it is lagging in nature. Source power factor in this situation will be lagging in nature. Source power factor will be lagging in nature. Okay. Now we are going to compare this mod VR and mod Vs. Compare mod VR value with that mod Vs. Look here. Mod VR value with mod Vs. Already you have the equation of Vs, right? Vs equals to cos beta L into VR plus JZC sin beta L into IR. And that IR you can replace with VR by ZL. IR you are replacing with VR by ZL. Now you can write it. VR is common. And you have cos beta L plus J sin beta L into ZC by ZL. You take up the magnitude of the sending end voltage, it will be mod VR into square root of. Kindly check, is it correct or not? Cos beta L square plus ZC by ZL square into sin beta L square. ZC by ZL square into sin beta L square. Like this you can say. Cos beta L square plus ZC by ZL whole square into sin beta L whole square. Simple. How is the value ZC by ZL? How is the value ZC by ZL here? Greater than 1. ZC by ZL number is greater than 1. Okay. So if this is greater than 1, look here please. Greater than 1 square into sin square beta L plus cos square beta L. Actually, in the previous case, ZL and ZC are equal. This ratio is 1. You can get cos square beta L plus sin square beta L. Cos square beta L plus sin square beta L is 1. So definitely we get mod VR and mod Vs is equal. Values is equal. But now ZC by ZL is greater than 1. So greater than 1 square into sin square beta L plus cos square beta L. This whole number will be definitely greater than 1. So greater than 1 into VR is equals to Vs. So I can say definitely this Vs value will be greater than VR. Vs equals to VR into a number more than 1. So Vs will be greater compared to VR. So as a Vs is greater compared to VR, definitely you can say the receiving end voltage magnitude will be less compared to sending end voltage magnitude. Receiving end voltage magnitude will be less compared to sending end voltage magnitude. You do the same sort of calculations for the current. After doing for current, you can observe that receiving end current will be greater compared to sending end current. you do the same calculations for the current, you will come to know that receiving and current magnitude will be greater compared to sending and current magnitude. Okay, so this is one discussion of keeping ZL less than ZC. Tomorrow we will discuss about ZL greater than ZC, ZL greater than ZC, and we'll draw some same sort of discussion. And finally, we make some sort of conclusion. And then we decide which loading is practical on the overhead line, which loading is practical on the underground cable. There ends the analysis, steady state analysis. Okay. So I'm stopping the lecture at this point. If you have any doubts, you can raise your hands now. If you have any doubts, you can raise your hands.
Sir, my first doubt is regarding surge impedance loading, sir.
Okay.
Sir, in surge impedance loading, whatever topics you have discussed right now, we have considered the loading, that is the load as resistor load.
Yeah.
But usually in practical scenarios, the loads we encounter are usually
that will be in distribution systems. If you talk about 220 kV lines and 400 kV lines, 75 kV lines, the load will be close to UPF only.
Oh, that is in the transmission.
In the view of 400 kV, 75 kV, 220 kV lines, we are discussing about these things.
Okay, sir. Okay, sir.
For those lines, load will be close to UPF.
Okay.
Even
so
though there is a change, there is a change, it may be close to 1 means 0.95 lakh, 0.96 lakh, like that you are going to get.
Okay.
So if you have decided some value of loading by taking this as a lossless line,
okay,
by a tolerance you reduce the value.
Okay.
For example, you have decided to keep a load of 400 megawatt on a particular line by using this pure lossless line resistive analysis.
Okay, sir.
Okay. Then if you go into practical line, it's a lossy line and the load is not exactly equals to UPF. Then you have to take up that load less than 400 megawatt, maybe let's say 360 megawatt, 370 megawatt, like that they are going to limit.
Okay. And this load, what you're saying, this for megawatt is in the distribution, I mean, from the transmission side, no, sir?
Transmission side.
Okay. Okay, sir. But sir, in transmission side, we usually don't encounter any loads. No? This voltage you connect it to a transformer, you step it down, and then only distribution side we see loads, no, sir.
Then that who is experiencing that load? Transmission line.
Oh, that entire thing is equivalently an equivalent model is almost an UPF load type loader.
Yeah.
Okay, sir.
Transmission line is loaded on the behalf of distribution line.
And the entire power system, that is entire this distribution side load, it sees as a
we are concentrating at only one place. We are concentrating at only one place at the end of the transmission line. Okay. That's what we said many times. If I say simply two buses like this, one side I will say source, one side I will say load. You should not feel that it's a generator exactly. Before this, we have a big network which is supplying power to this line.
Okay, sir.
Again, it's not a direct load for you. From this bus, you have many lines carrying some number of transformers, number of loads. The total we are combining and we are keeping it only one place.
All right, sir.
Okay.
Okay, sir. And sir, here, so if this impedance is same as that of root by L by C, we can prevent the usage of this compensation.
We will avoid the usage of compensation if you are maintaining voltage magnitude as equal throughout the length of it.
Okay, sir. And sir, next is regarding this wavelength. Sir, wavelength in the topics we mentioned as wavelength of the line, but usually isn't wavelength the parameter of wave as in?
You can take it, no issue. Parameter of wave, but measured in meters.
Okay, so the dimensions are the same. So we are taking it as the parameter of line. And sir, last one is regarding this energy transfer you mentioned in the first time around starting time. You mentioned about this energy transfer from the sending end to receiving end side. So that could how could you explain it, sir? Just how would
that we will discuss in transient transfers one time while we are switching that voltage onto the line, how that inductor and capacitors are getting exchange of energy.
Okay, sir.
That we'll discuss. But anyhow, as a basic term, what you have to remember is energy is going to be transferred from one place to other place via electromagnetic.
Okay, sir.
Means by continuous conversion of electric energy to magnetic energy to electric energy.
Okay, sir.
Without that conversion, energy transfer will not happen.
Okay.
Okay.
Sir, and last thing, the same thing. In this long line also, we have a significant effect of the shunt capacitance.
What is that?
In the long line, there's an L and we have a shunt admittance.
Yeah.
So my thing is, this shunt admittance will also draw some amount of current.
Yes, correct.
So wouldn't this L and C form a resonant type?
L and C resonant has to happen whenever XL equals to XC, but that's not the situation now, right?
Okay.
It's not a kind of resonance.
So there wouldn't be any
exchange of energies are exactly equal. Half LIM square is equals to half CVM square, we are saying.
Okay, sir.
That does not mean that XL equals to XC, right?
Okay. All right. Yes, sir. Because they are dependent upon the current and other parameters. All right, sir. That's it, sir. Thank you.
Yeah. Follow Vignesh.
Sir, my doubt is this surge impedance loading and ZL equal to ZC surge impedance, these are all applicable only in lossless system, or it will be applicable in lossy system also, sir?
We are discussing only about lossless system right now.
But practically, will it applicable in lossy system?
With a small change.
Okay, sir. And another doubt I have, sir, in steady state, that we need to proceed by lumped load system, sir. Will it be discussed in upcoming class, sir?
So till now, what system we are discussing in steady state?
In steady state, we are discussing the long transmission line distributed system, sir. I'm asking.
Distributed. Yes. What I have found for distributed?
ABCD parameters.
It's a two-port network model now.
Yes, sir.
That's what we have drawn here. This type of model I am discussing.
For load flow analysis also, can we apply this same
ABCD? I had in previous class also. This ABCD, we should convert it to pi model.
Oh, okay, sir.
That we have to use for load flow.
Okay, sir.
Yeah.
Okay, sir. Sir, can you please do one sum with that model, sir? But
I will do it. I'll do it.
Oh.
Yes.
Thank you, sir. That's.
Anil Kumar. Anybody have doubts? Please raise your hands. Tell me, Anil Kumar.
Sir, can you please explain the surge impedance loading, sir?
No, simply, whenever you are changing the load impedance value, power demanded by the load is going to be changed.
Yes, sir.
At the time, whenever you match the load impedance, exactly equals to surge impedance.
Okay, sir.
At that time, whatever the amount of power demanded by the load you have, that you are going to name it as surge impedance loading.
Okay, sir. Okay.
Else, it is the amount of the power flow in the transmission line by keeping ZL equals to ZC condition.
Okay, sir.
Okay.
Yes, sir. Sir, even varying the load, we should maintain that load impedance equal to surge impedance.
That's not the thing. It's a basic. It's a concept what we are saying. If you are keeping ZL equals to ZC, the loading is equals to SIL. That's the meaning.
Okay, sir.
Okay. So load is going
Thank
to
you,
change according to the consumer's demand.
Yes, sir.
Okay.
Okay, sir. Thank you.
Hello, sir.
Tell me, Pratima.
Sir, in this page itself, you have written effective load, no, sir? Can you explain that once again, sir?
What is the load on the source?
Resistive load, sir.
Do you have any interconnection between source and load?
No, sir.
Line is there, na?
Line, yes, sir.
Then definitely the source should satisfy the line requirement as well as the load requirement.
Okay, sir.
Then who is the load on the source?
Both, sir.
Both. That's the effective load.
Okay, sir. Thank you, sir.
Yeah. Any other doubts? You can raise your hands. Close the session.
Sir, 1 minute, sir.
Tell me, Balamukesh.
Sir, delta means it's an angle between sending end voltage and receiving end voltage, sir. Then
Yes.
what is beta, sir? Similarly, both are looking similar only, you know, sir.
Beta, what is beta?
Beta in surge impedance loading we have seen, sir. Beta.
Beta L.
The phase the phase displacement, but
Beta
both
L,
looks
beta L.
alike only also.
But for ZL equals to ZC condition, you are going to get the phase displacement exactly beta L.
Okay, sir.
But for ZL not equals to ZC, you don't get the delta exactly equals to beta L. It may be less than beta L or more than beta L. Chances are there.
Oh, okay, sir.
Hmm?
Okay, sir. Only in surge impedance ZL equal to ZC, the
ZC
delta
condition,
will be
you
equal
will be
to.
getting the delta equals to beta L.
Okay, sir.
In other cases, you may get it is more than beta L or less than beta L.
So we are considering only it as a delta in other
Delta,
cases.
yes, delta. Always it is delta.
Okay, sir. That's it, sir. Thank you, sir.
Okay. Imtiaz,
Good morning, sir.
tell me, Imtiaz.
Sir, for every line surge impedance will be same, no, sir, for 400 kVs.
Minor variation will be there because of L and C again. Even though we
Okay.
say L is almost same, C is almost same,
Yes, sir.
definitely there is a minor variation in the values of L and C, right?
Hi, yes, sir.
Because of that, there is a minor variation in the ZC value. Some lines may have 350 ohms, some lines may have 360, some lines may have 370. Like that, you have a small change. Single circuit lines. If it's a double circuit line, it will be almost half.
Okay, sir.
Because inductors will be in parallel, inductance will become half. Capacitance will be in parallel, capacitance will become double.
Yes, sir. Sir, one more doubt is, sir, in one of the questions is given as the two lines. One line have the 3 conductors, other line have the 2 conductors. One line has stated as a forward, other one is the
That I discussed,
return.
I think, in doubt session.
I think I not.
Inductance calculation.
Yes, sir. Sir, in the gap between the forward and return is 5.
That's okay. What's your doubt in that? What's your doubt?
Sir, I'm confusing, sir. Whenever I take the means bundle conductor.
You treat it as a
Yes.
double circuit line calculation.
But there is a given only 5-meter distance between 2 conductors.
Okay, whatever it is, even though if you have a bundle conductor system, on that bundle conductor system, if you apply double circuit equations, that will give you a perfect answer to you.
Okay, sir. Means the square root of the A1, A2, B1, B2.
Yes. Not
Okay,
A1,
sir, I
A2,
will-
A1, B1, A1, B2.
Yes, sir.
Mutual
Yes, sir. I
distances.
got-
Mutual distances, geometric mean you should take.
Okay, sir. I will take, sir.
Even for bundle conductor system also we can apply it. But you don't get a great variation. That's why we are neglecting the procedure and we are saying directly DAB equals to whatever the distance they have given.
Okay, sir.
Okay, you do it and send to me Telegram.
Okay, sir. I will send, sir. Thank you so much, sir.
Manivannan.
Hello, sir. Am I audible?
Yeah, tell me.
Sir, consider two-line conductor, one running in overhead and one underground. Will the velocity of both waves is different from another?
Different.
Okay, so sending and receiving current will be different because of the surge capacitance or some other.
Because of the charging currents, you can say so.
Okay, sir. That's it.
Yeah. Same.
Hello, good morning.
Tell us, sir. Good morning.
Sir, here written for beta L 0, 2 pi, then 4 pi. This will be shown going on for that calculation. But sir, what is the actually the wavelength is L? What is the meaning? The wavelength, the wave is a continuous manner, and in the lossless medium, it is continue up to infinity. What is the meaning of that? That wavelength is equals to L. Lambda is equals to L.
Wave is continued means what's your view there?
Means a wavelength means what is the wavelength? Wavelength is the from the 0 to 2 pi. What is the length? It is known as the wavelength.
That's for that you are defining for a sinusoid wave.
Yes, sir.
That's it. What is physical length of line?
L.
That's the physical length what you are saying. Then what's your doubt? Tell me.
Then I said that what is the actually meaning of that lambda is equals to L?
No, if you are in, no, not lambda equals to L. L equals to lambda.
Okay, L is equal to lambda.
If
Then
you are making your physical length of line is equals to lambda,
yes.
then you can experience that your sending in and receiving end side voltages are exactly equal.
Then it is a sinusoidal waveform for lambda means it is a sinusoidal.
Sinusoidal
Only.
waveform. Okay, okay.
Okay. Then there is a number of times the wavelength is repeating.
Number of times wavelength is-
Number of means the wave is continuous manner.
Okay.
Then what is actually L is equals to lambda? L is equals to lambda means what, sir? Actually, it is means a wavelength is how equate to the length of the physical length of the
You
transmission.
are increasing physical length of the line to be equals to wavelength.
Yes.
Okay.
Yes.
You are not
Then,
modifying lambda. You are not modifying lambda. You are modifying the physical length of line.
yes, physical
That's it.
length of.
Hmm.
Okay.
Physical length of line you are increasing, and that you are making it equals to lambda.
Okay. Okay. But means that sinusoidal waveform having one cycle which is having L length. Means for one period it is having length is L. That sinusoidal waveform has.
So this is the transmission line we have L length.
L, yes,
At this point, you have a sinusoidal wave.
yes,
It is x equals to 0 wave.
yes,
So it is, let us say, x equals to 1 kilometer length.
1 kilometer.
Wave will be shifted by an angle of beta.
Beta.
So you'll be getting like this, shifted by an angle of beta.
Yes.
Okay. And like that, it will be shifted continuously by an angle of beta towards the end.
Yes, sir.
Listen here. Whether that it's at certain amount of time t equals to it is t1, let us say t1 time.
Yes.
Time t equals to t1. What is voltage here?
Here, that is
Maximum.
V at an angle some
Maximum.
maximum.
Instantaneous voltage.
Okay.
I'm saying time t equals t1 na?
Uh,
Instantaneous voltage I am asking. Vm.
yeah.
What is voltage here?
It will be some minus
Less than.
less than. Okay.
It is t1 time, so it will be less than V.
Yeah. Okay.
And again, if you shift here, it will be even lower than this number.
Hmm.
Shifting here, even lower than this number. Like that, voltage is varying continuously.
Yes.
With respect to what?
With respect to for that time t barabar t1.
With respect to what the voltage is varying?
Voltage means
Space.
space. Okay.
We are moving on the transmission line from one place
Okay.
to other place
Hmm.
at a given time. At a given time. Okay, voltage is continuously changing. What is that voltage we are talking? Is it RMS voltage, peak, or instantaneous?
It is the instantaneous.
Instantaneous. Which is a more practical thing. Is it instantaneous, RMS, or peak?
It is instantaneous.
Instantaneous is practical always.
Okay.
RMS and peak values we are taking for our easiness in analysis, na, for a waveform.
Yes.
Instantaneous voltage is a practical voltage what we can observe. Time to time change.
Yes.
So I am saying you at a given time, if I stand at sending end side, if you look along the line, voltage is not same at all places.
Yes.
So voltage is varying with respect to space.
Yes.
Okay, now I am standing here only. X equals 0, I am standing. Just I am standing there.
Yes.
Now time is moving.
Yes.
At time t equals 0, time t equals to 0.1, time t equals to 0.2.
0.2.
Like that I am checking the voltage. Is it constant or varying?
It is actually varying.
Varying like this. Yes or no? Sinusoidal.
Yes.
So I can say at each and every point or at a given point, voltage is going to vary with respect to time.
Yes, sir.
So this voltage wave or current wave, whatever we are discussing, will experience two variations. One is a space variation, other one is a time variation.
Yes, sir.
Understanding?
Yes, sir.
Now, if you have the length is equals to, let's say, 200 kilometers.
Yes.
Okay, 200 kilometers. And this is x equals to 0 point, and this is x equals to 200 kilometers point.
Yes.
Now tell me, at a given time t equals to t1, instantaneous voltage at x equals to 0, instantaneous voltage at x equals to 200, whether these two are equal or unequal.
Instantaneous voltage will be equal because for line
Unequal.
unequal. Okay.
The phase shift is not equals to 2 pi.
Okay. But that
How much
phase will
phase shift you got? How much phase shift you got?
2 pi.
How much phase shift you got by reaching to 200 kilometers length,
2
line
by-
length phase beta L.
Beta. Okay.
What is the phase shift? Beta L. Beta is what? I think 1.05 something into 10 power minus 3 into 200 radians.
Okay.
Okay, it is not equals to 360 degree.
Okay.
I don't know whether you are understanding this or not.
Okay. Beta L na means that 2 pi is for what, sir?
If length of line equals to wavelength, then you get 2 pi.
Okay.
If the length is not equals to lambda, right?
Means it is for any x actually. Okay. X
Any?
is equals beta L. Understood, sir. Then-
Beta L. Okay.
Hmm.
So now listen. So how is the instantaneous voltage at x equals 0 and x equals to 200 at any time? Is it equal or unequal?
Then unequal.
Unequal. And if I extend this length of line equals to 6,000 kilometers, which is lambda,
Okay.
x equals to 6,000 kilometers, that is lambda. X equals to lambda. Then what you can observe at this place, this voltage will be in phase to x equals to 0 voltage.
Yes, sir.
Then at any time, if you check voltage at x equals to 0, voltage at x equals to lambda will be exactly equal.
Yes, sir.
That's a value.
Okay. Means okay, sir. Means for that it is varying like x and t. But in a there is some expression like in the electrical machine we are getting some cos omega t into cos theta, some term because
And all different things, and all not distributed things.
but
you think about
here,
only machine here, machine
okay.
there.
Here we can means x and t relation, any type of x and t in any of the expression we are not getting x and t relation actually.
No, we have not discussed about it. That does not mean that it won't have, right?
Okay.
We have discussed with respect to x. I think we have remembered. With respect to x, have I discussed?
Not in syllabus, sir.
No, with respect to x, have I discussed or not?
Yes, sir. X.
Where?
Okay. Omega t means
Where we have discussed about x?
for the transmission line.
Dx, ix.
Huh.
There we considered only space variation,
Yes, yes.
not the time variation.
Okay.
Time variation will also be considered. Definitely, it has to be considered while you are going for wave equations.
Wave equation. Okay.
That we are not discussing, not required. So that's why we are not discussing about the wave equations now. But I am saying you, we have a two variations. One is a space and other one is a time variation.
Yes.
Now,
Okay.
tell me, what's your doubt you have further?
Sir, now it is actually clearing. Means doubt is means what actually happening.
Actually, if I say all these things, it will be a bit of clumsy.
Okay.
Strictly speaking, if you stand at one point on the line, voltage is not constant at that point. It is continuously varying.
Yes.
Okay.
Okay.
And if I stand at one point at a particular amount of time, if you look along the line, voltage is not same along the line. Voltage is varying continuously.
Okay.
To take up that variation and all, we are introducing that angle.
Okay.
Okay. See, voltage magnitude throughout the length of the line, same I said earlier in case of flat line.
Flat line.
What is the meaning of that? RMS voltage magnitude is same at all places. That does not mean that instantaneous voltages are equal, right?
Okay.
Instantaneous voltages will vary. How you are showing the variation in your analysis? By using angle.
Okay. but that flat line that at every point that will be beta x. The angle is beta x something.
X is varying, right?
Means instantaneous is not same.
Not same. Because of the
Yes.
current will flow because of what?
Current is flow because of
Voltage difference.
Okay. Yes.
Current will flow due to voltage difference.
If instantaneous.
Yes, instantaneous voltage difference. To take care of that, we should put angle for the AC voltage all the time. While you are calculating current.
Yes. Thank you,
Okay.
sir. Thank
Yes.
you, sir. Thank you.
Pratyush.
Hello, sir.
Tell me, Pratyush.
Sir, how the receiving current can greater than sending and current?
You do with equation, Pratyush. Don't say with respect to charging current, applying KCL, KVL. It's a distributed model we are discussing.
Yes, sir.
Okay? Distributed model, you go with the equation of sending and current. Don't apply KVL, KCL.
So the equation it will be getting, sir, because that it will be act like ZL by
Which
ZC.
is original?
So
Which is original one? Which is original one? Is it application of KVL, KCL or equations?
Sir, the equation only because of distributed.
That's it. Equations itself is the original one. Means equations are saying that IR is greater than IS.
Yes, sir.
That we have to believe.
Okay, sir.
Okay. Polarity.
Hello, sir.
Tell me, Polarity.
At wavelength of transmission line.
What is it?
187 F.
I didn't understand what you are saying exactly.
Sir, my doubt is on wavelength of transmission line. Page number is 187, I think.
187. Okay, tell me.
Maybe 186. There you have taken that V in diagram, not V at the rate minus beta, angle of minus beta.
Okay, tell me.
Sir, how you taken that to minus beta, sir?
It is delayed, I said, right? Because after closing the switch at time t equals 0 plus, it will take some time to reach x equals to 1. So there is a time delay.
My doubt is on at the ZL equal ZC, you have taken V equal to mod VR at the angle of beta L. There you have not taken.
There the angles are different. Once sending end side is the reference you have taken there, receiving, sorry. Sending end side voltage angle you have shown beta L and receiving end side is your reference 0. You add beta L to this, you will get na.
Exactly.
You add beta L here, you add beta L here also.
Okay.
Reference is different in that case and this case. Yeah, getting? Yeah. Any other doubts? Please raise your hands. I think nobody's having a doubt. Thank you.